Gaia launched in December 2013. Its 5-year mission? To study the billions of stars in our Milky Way galaxy. Its first data release covered a mere 1 billion stars and the distance and motions for just 2 million. Now its second data release has updated this to an extraordinary 1.7 billion stars. The second data release of ESA's Gaia mission has produced an extraordinary catalogue of over 1.5 billion stars in our galaxy. Based on observations between July 2014 and May 2016, it includes the most accurate information yet on the positions, brightness, distance, motion, colour and temperature of stars in the Milky Way, as well as information on asteroids and quasars.
The data comes down to the ESA antennas on the S-track network in Argentina, in Spain and in Australia. From there it goes to Darmstadt, who control the spacecraft, and then it goes to our central data processing hub near Madrid in Spain, which is an ESA center. And from there it goes to the data processing consortium, which then slices it up in different parts and processes this into science products.
This new image, showing the distribution of stars in the Milky Way, represents 22 months of observations. 1.7 billion stars, their distance, motions and colour. The dark areas are not empty. They contain interstellar gas and dust.
So Gaia is measuring with 3 different instruments. It is doing astrometry, photometry and spectroscopy. So astrometry is measuring the positions, which helps to get the distances and also the motion of the stars. Photometry is essentially getting the color of the star, and color gives us the temperature of the star.
This stunning new image was produced by recording the color from stars and combining it with their overall brightness. We now know the position and brightness of 1.7 billion stars. Importantly, as well as the color, we also know the distance and proper motion of 1.3 billion stars, plus the surface temperature of 161 million, the radius and luminosity of 77 million, and the radial velocity of 7 million stars.
With spectroscopy, we are using one element which is based on Doppler effect. We are looking how the lines on the spectra are moving, and we get the speed of the star on the line also. But spectroscopy can be also used to analyze better the stars. So it is really the combination of all these elements. We know where the stars are, how they are moving, what is their temperature, and what are the properties of these stars. The most eagerly awaited result from Gaia are so-called parallaxes, which is the measurement which gives a handle to the distance of the stars. And this is a very tough measurement to be done. And we have known since Hipparchus, the previous ESA mission, distances to about 100,000 stars. And Gaia is going to increase that number to above 1 billion. So that is a real revolution.
The raw data from Gaia is used to create stunning visuals and animations. Obtaining the parallax measurement involved determining the apparent motion of the star by using 2 different vantage points along the Earth's orbit around the Sun, and separating it from the star's true motion through the galaxy. To do this, the spacecraft is orbiting around the L2 Lagrange point. The Sun, the Earth and the Moon are all roughly in one direction, and the sum of gravitational forces makes it an ideal position to study the stars at the dark side of the sky. Closer to home, Gaia observed 14,000 known solar system objects too, mainly asteroids. The quality of data provides us pinpoint accuracy over time of these orbiting neighbors.
So we have a multitude of targets. We have solar system objects, asteroids. Most of them are stars, but we also see external galaxies and quasars. And it is really different kind of science what you can get out from this. From the solar system targets, we can measure their positions extremely accurately. We will know much better than ever before the orbits of asteroids, for example. Stars we are using to understand our Milky Way better. From stars we get really the structure of our galaxy. And the advantage of seeing some quasars is that the reference system of coordinates is based on quasars because they are far away so they don't move. And we can observe them in radio. And now finally with Gaia we can see the same objects in optical wavelengths. So we can tie our radio reference system to optical one.
This animation of our own galaxy, the Milky Way, shows the roughly 100 billion stars. The location of the Earth's sun is shown here in one of the spiral arms. The Hipparchus survey is in red. It pinpointed the positions of more than 100,000 stars to a high precision. Gaia has surveyed up to 30,000 light years in all directions, encompassing 1.5 billion stars. Galaxies come in all shapes and sizes. Only one of them is our home. Gaia is opening up our part of the galaxy to help us understand the past, present, and future of our region of space. The first data release already produced hundreds of scientific results, but for astronomers across the world, the best is yet to come.
Essential thing of the Gaia mission is that the surprises will come later because we make the catalog and it is the scientists in the community who are going to utilize it and give the scientific surprises to us.
The Gaia mission is expected to be extended to 2020, which means not only cataloging more stars, but also examining possible exoplanets around them and even more surprises. A SpaceX Falcon 9 is ready for launch. The Falcon 9 rocket has proven its ability and reliability and become one of NASA's go-to launchers.
0. Liftoff. The SpaceX Falcon 9 carrying Tess, a planet-hunting spacecraft that will search for new worlds beyond our solar system.
Its payload is TESS, the Transiting Exoplanet Survey Satellite, NASA's newest exoplanet mission, led by MIT. It will find thousands of new planets orbiting nearby stars.
And visual confirmation as well of the fairing separation.
Crew 10 deployed.
TESS will eventually fly in a special, highly elliptical orbit that maximizes the amount of sky the spacecraft can image. It will expand its orbit until it can get a gravitational assist from the Moon. This slingshot will move it into a stable orbit that is tipped at about 40 degrees from the Moon's orbital plane. TESS will orbit Earth in exactly half the time it takes the Moon to orbit once. This feature helps stabilize the spacecraft against tugs from the Moon's gravity. The telescope will then spend most of its 13.7-day orbit observing the sky. As it nears Earth, it will rotate and transmit all its accumulated data to scientists on the ground. Over its 2-year mission, TESS will observe nearly the entire sky and potentially find thousands of new exoplanets.
The Transiting Exoplanet Survey Satellite is NASA's newest exoplanet mission. It's being led out of MIT, and it's going to find thousands of new planets orbiting bright nearby stars. And it's going to build upon the legacy of the Kepler mission, only it's going to focus on nearby bright stars that are sprinkled across the whole sky, and it's going to help us answer a really important question, and that is, which of our near-stellar neighbors has planets?
In those 2 years, TESS will look for signs of planets ranging from Earth-size to giants larger than Jupiter. TESS will search for these new worlds or exoplanets using transits, the same method as the Kepler mission. As a planet passes in front of its star, it blocks some of the light, causing a slight drop in brightness. TAS can detect these subtle dips and even use them to determine some basic features of the planets, such as their size and orbit.
The coverage of the TESS cameras is unprecedented in terms of the amount of sky that they can actually see at any given time, and also their ability to cover such a broad portion of the sky. The types of targets that TESS will allow us to find will enclose essentially all of the bright nearby stars.
Each of TESS's cameras has a 16.8 megapixel sensor covering a 24-degree square large enough to contain an entire constellation. TESS will watch each observation sector for about 27 days before rotating to the next one, covering first the south and then the north, to eventually build a map of 85% of the sky.
The thing that we're really excited about with TESS is the way that it'll actually build on the momentum that we started with Kepler. So TESS is going to take that same search approach, but apply it to the vast majority of the sky, which still hasn't really been looked at in detail when searching for exoplanets. And by focusing especially on planets that orbit bright nearby stars, TESS allows us to start looking at things like planet composition and atmospheric makeup. And that'll then be crucial when we want to start looking around stars that are even further away and in deeper parts of the galaxy as well.
This coverage, about 350 times what Kepler first observed, will make TESS the first exoplanet mission to survey almost the entire sky. TESS is the vanguard of a new era of exoplanet study and will forever expand our understanding of worlds beyond our own. The space telescope Cheops, characterizing exoplanet satellite, is ESA's follow-up mission. The telescope will study hundreds of known exoplanets using the transit method, measuring the dip in light as a planet transits its parent star.
When the planet goes in front of the disk of the star, then the light that we receive from the star decreases, right? And so this is what we want to measure, how much this light decreases when the planet goes in front of the star. And this is what's called the transit method.
Hundreds of known planets orbiting stars outside our solar system will soon be under scrutiny by Cheops.
We want to know what these planets are made of. We want to know how hot they are. We want to know the atmospheric composition, structure. We want to know the surface temperature. We want to know if there's water there, and eventually if there's life.
This is the Cheops instrument in a clean room at the University of Bern, where it was built, assembled and tested using electrical and optical ground support equipment and a thermal vacuum chamber. Cheops will measure the minute dip in light from a star when a planet transits across it. The size of the dip provides a direct measure of the ratio of the size of the planet and the star. This, combined with a knowledge of the size of the star, gives the planet's size. Radial velocity measurements from ground observatories will supply its mass.
When you have the mass and the radius, you have two very important things about an object, because you can get what we call the mean density after that. And that can give you a lot of information about the composition of a planet. For example, it can immediately tell you whether the planet is mainly formed of gas or if it's a rocky planet.
The telescope houses 2 mirrors, a CCD detector or camera, and a baffle to reduce stray light.
What makes Cheops unique, it's the only follow-up mission. So we are not aiming at discovering new planet, we are just aiming at going back to the ones we know and measure their size, either for the first time because it hasn't been measured yet, or improve the measurement that have been done in the past, either from the ground or from a space telescope with less precision.
The challenge was to build an extremely accurate and stable telescope that blocked signals caused by stray light from its electronics and instruments. The telescope will therefore be kept at -10 degrees Celsius and the detector at -40 degrees to reduce signal noise. The Cheops science team is currently selecting the best target exoplanets for further study. Other scientists will also be invited to submit proposals to use the space telescope. Now in Madrid for further launch preparations, launched from ESA's facilities aboard a Soyuz rocket, the Cheops will begin a new era of discovery. A recent analysis of 6 years of data from the MOA-2 ground-based survey concludes that exoplanets similar to Neptune in mass and probably composition are likely the most common worlds in the outer reaches of planetary systems. This data was achieved by a technique called microlensing. When a star passes directly between us and a more distant star, its gravity can act like a lens, magnifying the background star's brightness significantly for a few weeks. If the lensing star hosts a planet, the planet's gravity can produce a noticeable change in brightness over hours or days. This spike signals not only the planet's presence, but tells us its mass and distance from the star. Each method of finding exoplanets has different strengths. Radial velocity measurements reveal planets by detecting how they cause the star to move. Transit measurements reveal dips in starlight caused by planets passing in front of their stars. Both work best for massive planets in close orbits and for stars up to hundreds of light years away. Microlensing opens a planetary window onto a larger part of the galaxy, reaching thousands of light years. And because microlensing is more sensitive to smaller planets farther from their stars, it can reveal new planetary populations. In the MOA-2 study, researchers discovered that planets beyond a certain distance from their star tend to be roughly 20 Earth masses, or about the same as Neptune. That distance is what astronomers call the snow line, where water would be frozen during the formation of a planetary system. For our system, that location is roughly 2.7 times farther from the Sun than Earth. Beyond the snow line, where there is more solid material to coagulate and initiate the planet formation process, planetary formation is thought to be most efficient. In fact, worlds formed in this frozen hinterland may play an important role in making habitable planets closer to their star. The gravity of planets beyond the snow line can help send water-rich asteroids inward, where they can deliver water to young rocky worlds. To validate this theory, you need a space-based telescope with some unique properties. NASA's new telescope, WFIRST, is the Wide Field Infrared Survey Telescope.
Telescopes generally come into two different flavors. You have really powerful big telescopes, but those telescopes see a tiny part of the sky. Or telescopes are smaller, and so they lack that power, but they can see big parts of the sky. WFIRST is the best of both worlds.
WFIRST is the Wide Field Infrared Survey Telescope. What I think of WFIRST as doing is building on what were the two great successes astronomically of the 1990s and the last decade. That is the Sloan Digital Sky Survey and the Hubble Space Telescope.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences to launch in the 2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud, which is the nearest galaxy to us, or the stars in the galactic bulge. So you can do a much more complete accounting in a much shorter amount of time. The particular thing I'm interested in using WFIRST for is to actually do a statistical census of planetary systems in our galaxy. And what we're looking for is gravitational microlensing events. These are cases when another star passes in front of our line of sight to a background star, and it makes that background star get a little bit brighter due to the gravity of that foreground star. And that allows us to find planets.
What WFIRST will do is it will have what we call a coronagraph. A coronagraph lets us image and characterize really dim planets next to very bright stars.
No matter how good a telescope that you build, it's always going to have some residual errors. It's going to be the first time that we're going to fly an instrument that contains these high-format deformable mirrors that are going to let us correct for errors in the telescope. That's never been done in space before.
WFIRST will allow us to potentially make groundbreaking discoveries, finding out what dark energy is. So this will tell us if dark energy is an unknown form of energy or if it's a modification of general relativity.
Single WFIRST images will contain over 1 million galaxies, and we can't categorize and catalog those galaxies ourselves. Citizen science allows interested people in the general public to solve scientific problems. And so one of the things that I'm really excited about is enabling this bridge where the general public can get involved in doing actual science.
For me, it's a really exciting opportunity to play a significant role in a mission that I think will be one of the most powerful telescopes that we have in the 2020s and will be some of the most important things our country does in space in that time frame.
With these new eyes in the sky, there seems no limit to our ability to unlock the mysteries of our universe. NASA's latest robotic lander, InSight, descends to the surface of Mars. A challenging effort greeted with elation.
Touchdown confirmed.
Meanwhile, an orbiting ESA satellite, ExoMars, begins its own exploration of this enthralling planet. The majestic stereo imagery of Mars as seen from orbit reveals a planet of dynamic texture and form, slowly revealing its secrets.
We've sent a lot of missions to Mars in the past. We've sent rovers, we've sent orbiters, they've done a lot of really great science and a lot of really interesting measurements, but those measurements just scratch the surface of Mars. We know a lot about the surface of Mars, we know a lot about its atmosphere, and even about its ionosphere, but we don't know very much about what goes on a mile below the surface, much less 2,000 miles below the surface down to the center. And this will be the first mission that's going to Mars specifically to investigate the huge extent of Mars below the surface. The basic idea of InSight is to map out the deep structure of Mars for the very first time. We're going to map out the thickness of the crust, the size of the core, the composition of the mantle and core of the planet, sort of get the first map of the deep inside of Mars. It's going to Mars to do the science, to make the measurements that scientifically and personally I've been waiting for over 30 years for. As a graduate student, I was doing research on Mars, and I just needed to have the thickness of the crust. I just needed the thickness of the crust, and we didn't have it. And seismology was the way to do it. And so I thought, well, maybe someday somebody will put a seismometer on Mars and get this measurement so I can do my research. And so it's kind of an amazing journey for me to look back and say, I'm the guy who's actually going to put that seismometer on Mars, get that information, and now I can go back and finish the job I was trying to do 30 years ago. It's an amazing feeling.
The InSight mission will finally provide seismic information of Mars that scientists have been wanting since the very first Mars lander, Viking. It had a seismometer on it, but for a variety of reasons it never got back any seismic data. There's been many other attempts to get seismometers onto the surface of Mars for very good science reasons, but they've, for one reason or another, never been successful. So now we're right on the very edge of getting a seismometer onto Mars that will finally give us back seismic data. That seismic data is incredibly important to scientists because it gives them an idea of what the size of the crust, the mantle, and the core are, as well as the properties of each of those, which are the basic internals of every rocky planet.
The most fun or interesting thing about InSight from an engineer's point of view is really that we're playing the claw game super far away on Mars. We're taking this grapple and we're going to pick up an instrument and lift it up off the deck and put it down on Mars. So I like to say that we're playing the claw game on Mars with no joystick.
Next, a wind and thermal shield will be lowered over the seismic instrument to protect it from the environment. The second instrument, the heat flow probe, will be placed on the ground and over time will hammer itself down to take subsurface readings.
There's a lot of international partners on InSight. It really takes a whole world to produce an exciting mission like this. So most of our science missions are actually being supported by our international partners. So for example, the SEIS instrument, our seismometer, has support from the French, the Germans, the Swiss, the UK folks. So we have a variety of those people. The heat flow and physical properties probe is being provided by the Germans with some support from Poland.
InSight is a mission to Mars, but it's much, much more than a Mars mission. In some sense, it's like a time machine. It's measuring the structure of Mars that was put in place 4.5 billion years ago, so we can go back and understand the processes that formed Mars just shortly after it was accreted from the solar nebula. By studying Mars, we'll be able to learn more about Earth, Venus, Mercury, even the Moon, even exoplanets around other stars.
ESA's Trace Gas Orbiter mission arrived at Mars some time ago. Since then, this 3.5-ton spacecraft has been gently brushing the atmosphere to gradually adjust its orbit. In ESA's Planetary Missions Control Room in Darmstadt, Germany, flight controllers have been checking systems and commissioning instruments on the ExoMars Trace Gas Orbiter. Now it's ready to begin its science mission.
It has been a long time since we arrived at Mars in October 2016, and we have had a long, very long period, 1 year, of aerobraking, which consisted in reducing the orbital period from the time when we arrived, where it was actually several days, to 2 hours, which is the nominal period for science observations. I'm looking forward to the next few months enormously because the TGO will finally be able to show its full capability, the full capability of its instruments in terms of accuracy and the quantity and quality of data, pictures, spectra. And also because we will be able to do joint observations with our previous spacecraft at Mars, Mars Express, which is still alive and working after 15 years, actually. And for ESA, having 2 spacecraft around Mars in complementary orbits from a scientific point of view is very exciting and will allow certainly some very interesting discoveries and observations.
ExoMars will fill a double role when its partner rover is dispatched to Mars in the coming months in the search for life on the dusty planet.
It is a communication satellite on top of being a science orbiter. The so-called relay function allows us to communicate with all landers and rovers on the surface of Mars. At the moment, there are only rovers and landers from NASA, Curiosity and Opportunity. Some tests had been done already soon after arrival at Mars. And now we are going to start a campaign to calibrate and determine the best performance to relay data.
The Trace Gas Orbiter's primary mission, however, is to identify gases in the Martian atmosphere, particularly methane. First hinted at by Mars Express, and then by NASA's Curiosity rover as it sniffed the atmosphere with special sensors.
Well, we know that the lifetime of methane is very short, just a few hundred years. It will be broken down by the sunlight, by the UV ultraviolet component of the sunlight. So if it is there now, we know that it has to be refilled all the time. And where does it come from? That's the big question. It cannot be synthesized really in the atmosphere. It has to come from the surface or from the subsurface. But what are the processes that produces it? This is what we want to find out. One possibility is that it is some geological reaction between minerals and water. Another possibility is that actually also are microbes down buried underneath the surface that is producing it today or has produced it a long time ago, and they're all dead now, but that the methane has been kept underground and with some mechanism is released to get up into the atmosphere. So these are all these kind of things we try to find out.
By using the orbiter's powerful spectrometer, scientists hope to discover whether the methane comes from a geological or biological source. 95% of methane on our own planet comes from living organisms. The ExoMars rover, landing in 2021, will drill up to 2 meters beneath the surface to search for this evidence of life. And the rover, as well as NASA rovers and landers, will use the orbiter to keep in touch with Earth. Mars exploration is an international endeavor, and every mission adds to our understanding of this alien world, a place that some of us might someday call home.
Planetary exploration is always very exciting, but Mars, of course, has this very special thing, is that there is actually a place that you can imagine yourself walking on. You eventually, within not too far in the time in the future, surely people will be walking on Mars. And that makes it very exciting. And then to think about this idea that there might have been some kind of life, or even exist today underground on Mars, that makes it a very special place.
Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM.
Well, the SAM instrument detected a variety of organic molecules in a sediment that is from an ancient lake bed in the middle of Gale Crater. And what's important about these is that we now have a lot more certainty that there's organic molecules preserved at the surface of Mars. We didn't know that before. But what's interesting is that we don't know what the source of these organic molecules is right now. There's just not enough information from that. However, if we drill deeper and we look around a little bit more, we might actually be able to get to that information and tell, did they come from life? Did they come from geological processes? Or maybe they were from meteorites that were deposited in the lake. We just don't know right now, but hopefully we'll figure that out.
Curiosity is searching for carbon-based organics.
SAM made the new detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria.
Some other organics have been detected, like thiophene, which contains sulfur. Introduced by geological processes, this sulfur acts as a preservative, binding organic molecules together and making them resistant to oxidation, so preserving them for millennia.
Organic molecules could be the food for life, or they could be the product of life, or maybe they're from something altogether different, such as geology or meteorites that were deposited into the lake. We don't know what the source is, but there's a story there, and we're going to uncover what that is.
Scientists still don't know if the discovered organics on Mars are biological in origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. So for a time, Curiosity continued to travel, find interesting outcrops, drill holes, take samples. Then, inexplicably, something went wrong.
The drill's feed mechanism, which is responsible for moving Curiosity's drill bit into and out of rocks, didn't move when commanded. When Curiosity drills into a rock the way it was designed to, the drill's two stabilizer posts touch the rock first to steady the arm while the drill's feed mechanism moves the bit forward into the rock. Without the feed mechanism working, we can't drill that way. To solve this problem, we do what we always do. We worked it out in the test bed using Curiosity's twin on Earth. Our team of engineers and scientists have been working for months to figure out a way to collect and deliver rock samples without using the feed mechanism. Here's what we came up with. Using our new technique called feed extended drilling, the stabilizers are not used. The bit is now in a forward position extended past the stabilizers. Moving the drill straight into a rock and retracting safely without the stabilizers is challenging. We move the arm instead of the feed mechanism to place the bit onto the rock and press it forward as it drills. After making contact, we apply a light preload and drill a shallow pilot hole. We use a force sensor in the robotic arm to give Curiosity a sense of touch. This lets Curiosity adjust its arm motion and avoid getting stuck while drilling, kind of like you might adjust your arm while drilling into a wall at home. After drilling, we use a similar technique to retract from the hole without getting stuck.
With Rover 2020 design and construction well underway, engineers will be sure to avoid such a problem with Curiosity's cousin, which will land in the Jezero crater in 2020. "2020 will be a banner year for the exploration of Mars. In addition to the launch of NASA's Mars 2020 rover, the European Space Agency and Roscosmos are sending the ExoMars rover to the Red Planet. Rover 2020 and its companion helicopter will no doubt expand our search for life, past or present. However, the big advance forward in organic analysis will be the game changer. Both rovers will carry on board a MoMA.
The Mars Organic Molecule Analyzer, or MoMA, is the largest and most complex instrument on the rover. Its mass spectrometer subsystem and its main electronics were built and tested at NASA's Goddard Space Flight Center, which also contributed mass spectrometers to NASA's Curiosity rover and MAVEN orbiter. MoMA is designed with a mix of proven hardware and innovative new technologies. Here's how it works. In gas chromatograph mode, crushed Martian rock is put into an oven and heated to 900 degrees Celsius in just 2 minutes, vaporizing the sample. Molecules of hot gas rise up and flow into a narrow 20-meter-long tube. Special coatings inside the tube cause molecules with certain chemistries to slow down more than others, separating the mixture of molecules over time. Next, a beam of electrons ionizes the molecules, giving them a positive electric charge and deflecting them towards the linear ion trap. The ions are caught by a fluctuating electric field and sent to a detector to determine the chemical makeup. While gas chromatography has been used to study Mars since the Viking program, MoMA has a second method for preparing samples that has never been used on another planet. In laser desorption mode, a sample is placed beneath a powerful ultraviolet laser. A beam of energetic light builds within the laser and fires in a billionth of a second, concentrating its energy onto a spot smaller than a grain of sand. This rapidly vaporizes a portion of the sample, releasing large organic molecules that could be broken down by oven heating. The laser shot also ionizes some of the molecules, allowing the vapor to head directly to the linear ion trap. Neutral molecules are ejected by a vacuum, while the remaining ions are sent to the detector to determine their chemical makeup. Laser desorption will enable MoMA to detect long molecules, like lipids, the building blocks of cell membranes, a leap forward in the search for life on Mars.
The question of life on Mars is among the most important in planetary science, and the evidence may be buried just below the surface. With the help of MoMA, we will take one step closer to uncovering the answer. These images will pave the way to a new understanding of life in our solar system. CubeSats. They've been around for a while now. The domain of universities and institutions wanting to teach and gain experience in space. They're low cost, light, and very adaptable. Not only that, but they're also easy to send into orbit. Now, business is eyeing off these microsatellites with big plans for the future. The traditional satellite is an industrial and technological marvel. Designed and built from the ground up for a specific purpose with a long life expectancy, some communications and global positioning satellites are built on an off-the-shelf platform design to help alleviate costs. Launching them into orbit, however, is no easy feat. Weighing as much as 50 tons, they have to be placed in a geosynchronous or high polar orbit, which requires expensive launch facilities. The CubeSatellite, or microsatellite, devised as a training and development tool for university students, has now taken on a life of its own as a low-cost alternative to the conventional satellites in particular roles and for new purposes not previously considered.
A CubeSat is a nanosatellite basically in a box size. Standard dimensions of a CubeSat would be 10 by 10 by 10 centimeters, and you can have multiples of that unit. So you could have a 3-unit CubeSat, for instance, 10 by 10 by 30 centimeters, and all of the satellite equipment has to fit inside that box. The origin of CubeSats goes back over 10 years. In the US, university professors were looking for ways to allow their students to essentially build and fly satellite hardware during their degree courses. And so that was envisaged as a very low-cost way for universities to get their students well educated in the engineering skill.
University student teams from around Europe have been busy in the last months making the final preparations for ASIO, the European Student Earth Orbiter. ASIO is preparing the space workforce of tomorrow. The student teams designed, constructed and tested the essential parts for the mission.
During its whole project life cycle, ASIO engaged several hundred students, and already before launch we can say that it achieved all its main educational objectives.
Launched aboard a SpaceX small satellite-dedicated Falcon 9, ASIO was released into a polar orbit. Aboard the satellite there is a radio amateur communication system by the University of Surrey and AMSAT UK in the United Kingdom. This enables ASIO to transmit real-time data to schools and universities for science and engineering lessons.
I participated in the LMP project. It is a bit personal project for me because there is a component which I have in the design, and I wrote my thesis from this component.
I've been involved in the development and testing phases of the power distribution unit of the ESO satellite. It's an amazing feeling that your device will go up into space and it's ready, it's working well, and I'm so happy.
ESO, it's a complex system, and in the end I think it was challenging activity for all the payload teams. We had the chance to stay with them. We had the chance to teach them a few things that typically are not so common in academia.
ESO gave us the competence to actually build any scientific instruments here in the observatory. It gave us both the competence and also the connections with ESA, and we learned a lot from the projects in order to develop our further missions.
There's been some evidence that lightning produces gamma rays, and this is really the first satellite that's going to go out and investigate if and how and where and everything associated with gamma rays coming from lightning. There's been evidence, and others have seen this, but again, there's never been a satellite dedicated looking down at Earth for these terrestrial gamma ray bursts.
We want to make artificial signals similar to lightning and see what the board does, make sure it's filtering those signals the way we want.
We're going to put it into HDL code and then get it through this chip.
One of the tenets of the CubeSat program is to involve undergraduate students at all levels, from design to building to some of the theory, data acquisition, every aspect of this. So we're really training here the next generation of space scientists, of satellite engineers. As soon as the launch goes up and they know they're a part of that satellite and data's coming in, I mean, that'll be with them throughout their life.
Where else could CubeSats be applied? A major space mission to Mars, InSight, was a perfect opportunity to test out some new technology.
Liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites and generates more than 860,000 pounds of thrust.
Flying with the InSight spacecraft to Mars were two CubeSats. Called Mars Cube 1 or MARCO, they were a technology demonstrator and the first use of miniature modular CubeSat spacecraft design in deep space. The pair of briefcase-sized spacecraft, MARCO A and B, were launched on the same rocket as InSight and traveled independently of the main craft. They carried a number of communication and navigation flight experiments. Although NASA emphasized the experimental nature of the CubeSats before the InSight landing, the MARCO spacecraft performed as intended, receiving the UHF telemetry from InSight during its entry, descent, and landing phase, and rebroadcasting it at X-band frequencies received by NASA's Deep Space Network. This vindicated CubeSats as another tool in the exploration of deep space. To top it off, MARCO B managed to take a photo of Mars and transmit it back to Earth as it passed by the planet. The rush to exploit CubeSats is on. Scientists and engineers have begun designing, building and launching various designs for specific missions and for testing new technologies in space. Rocket launching companies have been quick to respond, developing and flying dedicated launches for the emerging small satellites market. SpaceX and ESA's Vega launchers are among these companies, while the Electron from Rocket Labs has already begun flying commercial CubeSat launches and is planning a monthly service.
My involvement goes back 10 years from when I was working in the education office at ESA. So indeed, I was responsible for managing university CubeSat projects that we would then later fly on the maiden flight of the Vega launch. We had 7 CubeSats that flew on the Vega maiden flight, and actually many students were involved in those projects, and they went on to graduate, and many of them formed their own spin-off companies, which now forms the basis of the CubeSat industry today. What we're seeing is that the same technologies that are being exploited terrestrially for aerial drones are also being exploited by CubeSats. So I like to think that that same technology will enable CubeSats to become the autonomous drones of the space domain. With the capability of CubeSats to become autonomous space drones, they will have the performance to be able to perform autonomous navigation, close proximity operations around other target objects, and also be able to fly in swarm formations. So these are very advanced architectures. We might also see them being able to perform autonomous rendezvous and docking together, forming building blocks to build up larger structures in space in the future. When we do the CubeSat projects, of course, the standard engineering approach combined with the access to ESA facilities and technical know-how gives an added value to ESA member states to ensure that we maximize the probability of mission success within the tight financial constraints of each project. So far, we've flown one technology CubeSat in orbit, GOMX-3. That mission has been very successful. It's recently re-entered the atmosphere, so the mission has been completed successfully. Now we are preparing to fly another CubeSat called Carmen. It's designed to demonstrate re-entry technologies, very exciting and challenging project. And beyond that, we have another 4 technology CubeSats in development, and we're already talking to our member states about starting many new projects in the future for these technology demonstrations.
The use of microsatellites for commercial and industrial purposes is a growing field of interest, as is the concept of the Internet of Things. One company has combined the two into what may become the next great technological revolution. Alongside household names like Microsoft, Google, and SpaceX, you may soon be adding Fleet to the list.
So Internet of Things is a concept that probably started 5 to 10 years ago. You know, people were talking about this. There are 25 billion devices coming online in the net. It's the 4th industrial revolution. Everything will be connected. It's going to change our lives. I kind of separate the concept in 2. The smart cities. So when our life will change into buildings, you know, your Fitbit connected to your fridge and your car driving itself, and the smart fridges, and smart traffic lights, and so forth. And also smart industry. So what happened in remote areas, in a big farm or in a big oil and gas company, a big mining, that's a heavy industrial revolution. So Internet of Things is the idea that we are kind of changing the way we operate. We have spent 40 years connecting people and, you know, bringing computer inside factories, and suddenly everyone has got a computer that cannot live without it. You know, if there's a day you cannot use a computer, you go home because what am I supposed to do? So in the next 40 years, things will change the industry in the same way the computer did. So imagine a big farm, suddenly everything will be connected, you know, from the soil to the literally soil, you know, content to animal tracking, weather station, thousands of sensors that we allow the farmer to literally understand so much of the way they operate that we will solve the biggest problem on earth, you know, water leakages and drought and so forth. But that goes into, you know, transport and logistics, not measuring pallets and fruits traveling all over the world. I think we waste 60% of our food in supply chain. So there are big changes happening, and this is all about little sensors being connected. The problem is that this big industry that I'm mentioning, they have not 3G. I mean, 3G, 4G, even 5G covers the population, but 95% of the world is unconnected. And this is where our farms are, where our mining and oil and gas company are, where the shipping containers are. So it's a kind of a problem that terrestrial infrastructure cannot solve. And well, we got space, or we solve it from space.
The potential for a constellation or swarms of CubeSats to become powerful research and communication tools is now starting to be explored. The ability to track almost anything across the planet is now a reality. The possibilities seem almost endless.
Internet of Things is interesting because with one satellite in LEO, so low Earth orbit, you cover almost every side of the planet. And customer sees you once a day. It's not much. You know, it's not really good for high-speed internet or talking Skype or checking YouTube, but it's great, you know, for a valve. or a soil moisture sensor, or a cow. You don't want to know where a cow is every single minute of your day. Probably you do, but once a day is perfect for Leo. But when you reach 100, or for us it's 100, it probably will be even less, the latency is so good that you can actually tackle some high pressure emergency applications like safety and security, in which you want to send the data and grab it straight away and send it to the customer straight away. But the good things of Internet of Things is that you launch one satellite and then you're in operation. You can serve everything now. So we had launched 4 satellites last year. It was a great journey at Fleet. For a startup, we launched them in 24 days. 2 with Rocket Lab was first Rocket Lab launch of nano satellites was commercial. So it was literally like, what is going to happen here? And then of course SpaceX and PSLV, but the first satellites we built was almost 1 year, the second one 2 months. When we launched with Rocket Lab, by the time we start building the satellites, to the time we booked the flights and the time we were in space, was 4 weeks. So it's a big revolution also on the launcher side. They can put us in space quite fast.
This startup company seems to have hit the nail on the head. Low-cost terrestrial sensors can be hooked up to almost anything, and their status uploaded to the CubeSats for transmission to the clients via the net.
The people that are booking these sensors, they come from the biggest oil and gas company in the world, with all the farms in South America. This is big customer. So we are entering a phase in which, as most startups are starting so little, is having massive customer impact. That satellite company that operates for $1 billion in many, many years don't have. So it's time to see at these satellites and understand it's not a game anymore. This is going to be $1 billion companies very, very fast. So it's quite exciting.
This system could increase efficiencies and save waste across the globe.
Earth needs help. Earth needs monitoring, Earth needs efficiency, Earth needs water to be saved, and food to be not wasted, and people to be safe. So millions of sensors are going to change the world forever. It's going to be billions. When we started Fleet, we started with a dream of connecting the entire world and millions of devices. We call it 1F. It's our first constellation, and for us 2F is going to be the moon, and 3F is going to be Mars.
The potential for space exploration is exciting. Quick and efficient data networks dispatched to the Moon, Mars, and beyond, or even swarms of CubeSats surrounding an asteroid or a spacecraft during rendezvous, sending back data and video. The scope is limitless.
Imagine you can have a constellation to track every robot and things just to make sure where they are, and this is just the beginning. And the reality is that when the big entrepreneur will go to Mars, they will put so many things, and you want to make sure they're tracked, and it's a complicated exercise. And a CubeSat, it's a way to go there fast. When you need to move a big satellite to Mars, it takes a long time. And you launch a storm of these, eventually they will get there. But eventually we'll go there, and we will have to do the same. We will have to have big responsibility when we start conquering the other planets, monitoring what happened. I think, it's going to be Fleet responsibility as well, I guess.
The American relativist John Archibald Wheeler succinctly explained Einstein's equations on relativity this way. Space-time tells matter how to move. Matter tells space-time how to curve. For theoretical scientists to move forward, Einstein's equations now need to be either proved or disproved. Two fundamental rules of the universe, as theorized by Einstein, are that light in any form moves at the same speed, meaning that space-time is smooth, and secondly, that the laws of physics are the same everywhere in the universe at any time. Since the more recent discovery that the universe is expanding at an accelerating rate, other theories counter to Einstein's have been put forward. One suggests that space-time is lumpy, and that higher energy light will feel it more as a hindrance. To put this theory to the test, scientists needed to compare the speed of two particles of high energy light.
So you might be thinking, two tiny particles of light, why is that important? Well, you need to take the very large and the very small together to understand the universe as a whole. So far, Einstein's theory of relativity, which describes space and time as a smooth fabric that's distorted or bent by massive objects, has been a spectacularly successful explanation of gravity and the large-scale behavior of the universe. Whereas quantum mechanics, another spectacularly successful model, describes the workings of atoms, subatomic particles, and some of the fundamental forces of nature. But scientists have never been able to reconcile the two. Both relativity and quantum mechanics are equally fundamental in their own regimes. So scientists want to find a theory of everything that describes the universe as a whole.
Several ideas which attempt to reconcile relativity and quantum mechanics suggest that space and time are not actually smooth and uniform, but are instead a seething froth when seen at the smallest scale, like bubble wrap. A low-energy, long-wavelength photon is unaffected by the lumpiness of space. But a high-energy, short-wavelength photon is hindered by the froth. This makes it move more slowly than lower-energy radiation, so it breaks Einstein's law that all light particles must travel at the same speed. To test this theory, they needed Fermi, the orbiting gamma-ray detector.
We observed a gamma-ray burst. A gamma-ray burst is a huge explosion. That gamma-ray burst produced a large number of photons, one of which had enormous energy, very short wavelengths. Those photons traveled 7 billion years to reach us, and yet the highest energy, the shortest wavelength photon, arrived within 900 milliseconds of the lower energy photons. That's a little bit like racing two speedboats, one through water and the other through molasses, and having them arrive at the same time. It just doesn't happen. Because Fermi saw no delay in the arrival time of the two photons, it confirms that space and time is smooth and continuous, as Einstein had predicted. And it shuts the door on several theories of everything that had predicted that space and time might be foamy enough to interfere with light. And the observations that we've made of these two photons with Fermi takes us one step closer to achieving the goal of having a theory of everything that combines the most successful aspects of quantum mechanics and relativity into one unified theory.
Einstein's theory also predicted that gravity could bend light, an astronomical effect as seen here called an Einstein ring. Gravitational lensing is where the light of a galaxy behind another gravitational body is bent around it, forming a ring of distorted light. But do the numbers add up? And can the mass of the interfering object be measured using this theory?
So we've known for a long time that on the scale of the solar system, general relativity is either the correct theory of gravity or extremely close to correct. But we don't actually know whether general relativity is the correct description of how gravity works on the scales of individual galaxies or of the universe as a whole. So we used two phenomena. One is called gravitational lensing. So general relativity says that when you have a massive object like a galaxy, that causes space-time to be deformed. And that warping of space-time means that if you have a second galaxy behind it, the light coming from that second galaxy will be deflected. And if the deforming of space-time is enough, you can get multiple images of that background galaxy warped into what we call an Einstein ring. And the radius of that ring, how big that ring is, tells you how much warping of space-time is going on. So we used 2 telescopes to do this. We took an image of the gravitational lensing using the Hubble Space Telescope, and that let us measure how big the Einstein ring is. And then we used the very large telescope operated by the European Southern Observatory in Chile to measure how fast the stars are moving in the lensing galaxy. So we took spectra. This is measuring how much energy is emitted basically in each color. And those spectra tell us how fast the stars are moving in the galaxy. Measuring how fast the stars are moving tells us how much gravity there must be holding those stars in their orbits. And so comparing the amount of mass that we infer from that with the amount of warping of space-time that we see from the lensing, we're able to test whether the amount of warping is consistent with general relativity.
In 1917, Einstein created the concept of a cosmological constant in his calculations to balance out gravity in his theory of general relativity. He later abandoned this concept, considering it erroneous. However, with the recent discovery of an accelerating universe, that constant might help explain dark energy.
Dark energy is a hypothetical substance that explains why the expansion of the universe is accelerating. So the universe has been expanding ever since the Big Bang, but what's odd, and we've only known this for the last 15 years or so, is that acceleration is getting faster. It's accelerating. Now, naively, you would expect that all of the gravity in the universe, all of the mass, would cause things to pull together and slow down the expansion or have it carry on going at the same rate. You can't really come up easily with a way of explaining why the expansion is getting faster and accelerating. Now, one way of explaining dark energy, one way of getting rid of dark energy entirely, is to say, well, all of that interpretation is based on assuming general relativity is the correct theory of gravity. Now, if it's not, and a lot of theoretical cosmologists have worked on this in the past, you can come up with ways of accelerating the expansion without introducing a dark energy. Now, our work, which we found that general relativity is the correct theory on the scale of individual galaxies, tells us that if you want to explain away dark energy, you have to maintain the validity of general relativity on astronomical length scale.
Another factor of Einstein's relativity is that gravity and space-time will function in a predictable manner everywhere.
The whole theories about the formation of the universe, how the universe is evolving, are based on one philosophical and fundamental assumption, which is that the laws of physics are valid everywhere in the universe and at any time in the universe. While here on Earth, we can only prove those laws of physics now and on certain circumstances. So it's very important in astronomy to also check that those laws of physics are still valid, where the gravitational fields are much stronger.
Recently, it has become possible to put that theory to the ultimate test. The effects of Einstein's general relativity will be assessed in the most extreme gravitational conditions imaginable, at the heart of our own galaxy.
We think we know that this object we have in the galactic center is a black hole, but to prove that, without any doubt, we have to come so close that we actually have to measure the fabric of space-time and see that it's that which the theory of Einstein predicts. So that's the concepts. Then comes the question of difficulty, and I have to say, ooh, that was a long path. It was very, very difficult because while gravity is sort of an obvious thing, you stand here on Earth and you sort of have an idea what it is. In reality, it's an extremely weak force, and the effects of general relativity are extremely small. So you have to measure to a precision which we are normally not used to in astronomy.
Well, you see, the center of Milky Way, where we suspect there is a black hole, has stars orbiting this central black hole. And these stars are measurement objects, if you like. They test the gravity of the object. And there's one star in particular, which we've been following now, believe it or not, for 25 years. That's more than half of my scientific career, with telescopes here at ESO in particular. And we've charted the orbit of this star, and we know that around this time, this star will make it as close as 4 times the distance of Neptune to the Sun. That's 17 light hours. So that's very, very close. And that's the unique opportunity to, in fact, test out the gravitational theory, because there gravity is the strongest. The star now moves with about 3% the speed of light, or several hundred times the speed of the Earth around the Sun. And that's when these tiny little warps in space-time, which cause general relativity to be different from Newtonian theory, to be most pronounced. So it took us about a decade between 1990 and 2000 to basically come up with robust evidence for this mass. And then in 2002, nature gave us just an absolutely miraculous star which moved so close to this object that you could see it zip around the mass in a matter of only a few years, and that gave us absolutely fantastic information. We could estimate the orbital parameters, the mass, etc., and we were fairly sure it's a massive black hole. Now the orbital period of this star is 16 years, and these measurements we took here on the then new Very Large Telescope we took in 2002. Take 16 plus 2002, and that's 2018. So our star is coming back to its original, very close position near the black hole. That's the time when we want to be there and make these measurements.
Preparations for this breakthrough observation began in early 2018 at ESO's Paranal Observatory. Their cutting-edge astronomical equipment was readied to make measurements of one of the most extreme gravitational laboratories at the center of the Milky Way.
For the discovery, a combination of 3 instruments of ESO were used: NACO, Symphony, and Gravity. And all of those instruments are unique in the world. NACO is adaptive optics in the infrared. We don't have so many in other telescopes. Symphony is a high-resolution spectrograph, very important to measure at which speed the star is coming to us or going from us. And Gravity is an interferometric instrument, the only one in the world that can combine 4 big telescopes, 8 meters telescope, with a baseline of 130 meters, so having the same resolution as a 130-meter telescope. And it has, in addition, the capability to do astrometry, very accurate astrometry, so it measures movement that are the equivalent of an astronaut on the moon moving a flashlight by about 10 centimeters. And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
So by testing, by measuring these predicted physical teeny effects, they are a very, very small fraction of what we knew so far. That's why we have to make such precise measurements. That's how we can test general relativity in this domain.
We need to get very sharp images. And the best way we can get sharp images is to make big telescopes. But since we don't have these very big telescopes, we combine telescopes. We create a super telescope, in this case, which is 130 meters in diameter.
Even with the impressive size of the Very Large Telescope, the only way to precisely measure the path of the star around the supermassive black hole took some innovative telescope teamwork.
For our work so far, what we've done is we've taken pictures with the single big telescopes, the single 8-meter telescopes, and make them as sharp as you can be. The problem is, and you see this in my hair, there's wind. And the wind distorts the waves. And so either you go out in space very difficult for an 8-meter telescope. Or you take the 8-meter telescope and you repair the distortions which the Earth's atmosphere does. Like on a hot day when you travel along a road and you see the flimmering of the distant approaching cars. So that's what we do. That's called adaptive optics. And that makes the images with single telescopes already very sharp. But that's not sharp enough for what we want to do now. We really need to make still better, still 10, 20 times sharper images to see the tiny effects of general relativity. And that we do by taking into account that ESO not only has one telescope, but 4 of these gigantic 8-meter telescopes, and we can bring them together as if it's one. That's a very challenging experiment, but we've done this now, and so we are ready to make these measurements at an unprecedented precision.
So we combine the light from 4 telescopes, the very large telescopes, here in the center of the mountain of the observatory. The 4 telescopes are separated by 130 meters, which means that our super telescope can make 20 times sharper images than a single telescope.
So we have all 4 telescopes working together, and in addition to these 4 telescopes we have a beam combiner, and this combines the light from all the 4 telescopes, and this is gravity. Gravity is, of course, it's the best, because we can really trace the orbit of this star very, very carefully with really good accuracy, so we can now get very nice orbits, and we're trying to test all our theories with this very nice data we have now.
2 other state-of-the-art instruments will reveal an effect called gravitational redshift. This is visible when light from the star is stretched to longer wavelengths by the very strong black hole.
We actually expect that we can see general relativity, and how can we see that? It's actually a slight deviation of how the star is moving, and this deviation we can see in the first place with the so-called Doppler effect. It's currently approaching us, and it will fly away, and this Doppler effect is actually something we can observe by the means of spectroscopy, and spectroscopy in turn means that you need a spectrograph, and such a spectrograph is Symphony, and that is the instrument which will be the one which actually is observing the relativistic effects.
Now, after an epic 26-year observing campaign, the effects of Einstein's general relativity have been clearly seen for the first time.
So the experiment we're doing is extremely simple in some sense. We are just measuring the motion of stars around the black hole. That is very much like Earth goes around the sun, and you can actually calculate the mass of the sun from the knowledge that Earth takes a year to go around the sun, and essentially we try to do the same. We try to measure the mass of the black hole by seeing how the stars fly around it.
And right now we are observing this passage as the star moves into this critical curve around the black hole.
For scientists, a spectacular show of orbital mechanics and relativity.
So what were the most exciting moments in the observing campaign? I think actually it was in the very beginning, about 2 years ago, when we for the first time pointed to the black hole and to the star, and actually we've seen that both of them, and this was a big surprise for us, because we did not expect it. Actually, it's right at the field of view of what we have, and so this was very revealing to actually see it, that we can go to very faint, that we see the faint black hole all the time and the star nearby. And the other most exciting probably was that this year, when the star was moving so fast at a fraction of the speed of light, that you could see it from night to night. This was very exciting to see.
And the combination of all these instruments, interferometric and classical spectroscopy, adaptive optics, is what makes ESO unique. It's having all of them on the same side in a position where you can observe the galactic center in good conditions.
The beauty of it is that it's a very simple experiment in the phenomenon. Yeah, there are some technical challenges that you have to overcome to build the instrument and perform the experiment, but the concept is very simple. you can probe the black hole properties, and then you can probe the gravitational field, which is a very strong one. And up to now, when whatever tests for the general relativity or this geometrical theory of gravity that we have has been in the solar system, and also some pulsars, but in this very strong regime, it has not been tested. So this is just a starting point for it with the developments like instrument developments and the new telescopes. We will do more and more of this.
More than a century after he published the paper setting out the equations of general relativity, Einstein has been proven right once more with the combined resources of the ESO.
This is one of the huge benefits of ESO, and the way ESO works is that there is always a very strong collaboration between ESO and its institutes in its member states, which is very unique in the world because it enables ESO and the ESO members to undertake projects like gravity, which are so complicated that you need a strong team.
Well, what comes next? For the next years, we have a pretty good outlook of what will happen. So the next effect, which we will see, is a Schwarzschild precession. This means the orbit of the star will rotate. The ellipse will rotate a little bit. And so this is an effect which we will see next year. Pretty sure about it. Then we come to more subtle effects of general relativity, but even more exciting. This is about the space-time itself around a black hole. So the space-time around a black hole will rotate with the black hole, and so this will move the orbits of the stars yet in another direction. And this is very exciting because this property is very unique to general relativity, and we will only be able, in that black hole in the center of the Milky Way, will have the precision to measure that.
With the theory of relativity dusted off and placed back on its pedestal, what remains is for scientists to work out what dark energy is and how it affects the known universe. We are finding more and more exoplanets, more and more locations for liquid water, and the possibility for life as we know it. But where are the alien civilizations? Where are the technologically advanced creatures? Why can't we find signs of other sentient beings? Where are their signals out there amongst the stars? Perhaps the answer to that age-old question, are we alone in the galaxy, is a yes. American astronomer and astrophysicist Frank Drake established the search for extraterrestrial intelligence, or SETI, back in 1960. Listening to the stars and the noisy galaxy, trying to find signals that are deliberate, messages from other planets where life has evolved an intelligence, a technological civilization like our own. able to comprehend the vastness of space. Like us, looking for the answer to that age-old question, are we alone? There are 3,700 known exoplanets so far. NASA's TESS is going to find lots more. The European Cheops mission will specifically study the known exoplanets and look for more around our brighter stellar neighbors. Multiple planetary systems and terrestrial, Earth-like planets are coming up trumps, and we've only been looking for 15 years. We have been looking and listening for nearly 60 years now with zero results. No radio signals, no laser or other light flashes in our direction, no attempts at communication that we can detect. So where are all the aliens? Well, it's a complicated question. Stars that can harbor Earth-like planets, viable exoplanets that can sustain liquid water. As for life, how long does it take to generate life? Then, how long to evolve into intelligent life? Will that intelligent life become technological? How long will an advanced civilization survive? Tough questions when you only have Earth as your example. Then there is the time factor. The universe is 13.8 billion years old. Our star, the Sun, is 4.6 billion years old, and probably a third or fourth generation star. Earth is 4.543 billion years old. Our moon is just the right size to stabilize Earth's rotation and provide ocean tides and sea currents. Life on Earth is at least 3.5 billion years old. Several major climatic and asteroid interventions steered the evolutionary cart leading to us, Homo sapiens, 200,000 years. Our civilization began around 6,000 years. The industrial age is just over 200 years. The ability to send signals into space, maybe 100 years. Powerful radio signals, television signals, radar and laser light, say 50 years. Being generous, our signals have traveled out in a sphere with a radius of 100 light years. That's about 1,000th the width of the Milky Way, which is 105,700 light years across. The nearest galaxy is Andromeda at 220,000 light years away. How long will we continue to broadcast? In other words, how long will our technological society last? Some think not so very long. We have to be realists. There will not be too many terrestrial-like planets with liquid water and an atmosphere to support life, nurture that life to evolve over billions of years into a sentient species that may just develop technology and an understanding of the cosmos to want to listen out and respond to a signal from space. There is most likely life out there, but it's not talking to us yet. Let's crunch some numbers. We'll take the arbitrary figure of 100 light years, where a sufficiently advanced society could detect our radio signals. They then work out where the signal came from and dispatch a response. This could take a few years to achieve. Then that signal will take up to 100 years to get back to us. 100 light years in kilometers roughly equals 9 plus 14 zeros after it. What stars are within that reach? We're only looking at main sequence stars, ones that are stable and long-lived, moving through various stages in their lifetime of billions of years. So we have 3,868 stars to choose from, plus a few more very dim ones we haven't found yet. Exoplanet hunters have been targeting the dimmer, smaller stars called red dwarfs or M-type stars because it is much easier to detect planets around them. There are 2,026 stars of that class in our region. They have also been looking at the slightly larger orange K-type main sequence stars. Because of their spectral and luminosity qualities, astronomers favor them for having habitable Goldilocks regions. There are 947 and counting, though there are only 155 within 50 light years. Then there's the G-type stars. Our Sun is a G-type, so they are highly regarded for habitable zones. There are 512 of them. F-types are slightly larger than our Sun, 303 are nearby, and several have known planets. A type which are young stars, a mere 100 million years old, and again have been found to harbor Jupiter-like gas planets, 76. B-type are giant blue stars and rare, only 4 in our region. And supergiant O-types are hot and hostile and nowhere near us. So, how many exoplanets? 3,700 confirmed exoplanets so far. Five Mercury-sized rocky worlds, 72 Mars-sized, 701 Earth-sized terrestrials. (982 called super-Earths), 799 Neptune-type gaseous worlds, and 1,217 Jupiter-sized gas planets. So that gives a current total of 1,683 Earth-like rocky planets. How many of these rocky worlds could harbor liquid water on their surface? Well, there is the habitable or Goldilocks zone around these stars, where the planets receive the right amount of solar flux, where water is liquid. Too close and the water would boil away. Too far and it will freeze, making life more difficult to evolve. So, scientists have estimated there are 17 definitely within this zone. but 3 are outside our distance limit of 100 light years, so that leaves 14. Plus another 13 terrestrials that could seed life, but be very harsh and unforgiving to it. That makes 27 candidates capable of harboring life as we know it.
Life could be incredibly common, because there are lots of planets out there, or it could be an incredibly rare event that only happens, on 1 in a billion planets in a galaxy. We really just don't know. So whenever I get asked that question, my answer is, I don't have an opinion yet. I'll need some more evidence.
TRAPPIST-1, an M-type dwarf star at 39.6 light-years distance, contains a solar system of 7 terrestrial planets and is a major contender for harboring liquid water. They're all Earth-sized candidates. Other multi-planet systems in our region include HR 8832, 55 Cancri, and 61 Virginis. The names just roll off the tongue, each with at least 3 planets orbiting it.
Well, looking at exoplanets, these planets around other stars, is a bit like detective work. They're so small next to a bright star that it's hard to tease out information unless you do it incrementally. So what we can tell right now is that these planets are, in fact, similar to Earth in size, and we can tell that some of them may be similar to Earth in its composition. Doing kind of crude studies of the density of these planets. We're also using the Hubble Space Telescope right now to do follow-up observations of the atmospheres of some of these planets to see the composition of the atmosphere and wondering and trying to find out if maybe there might be water in the atmospheres to see if they are similar to our own Earth's atmospheres.
With names like TRAPPIST, Tau Cetus, Gliese 876, HD 219134, and Wolf 1060, these exoworlds sound ponderous and uninteresting. But one day they may be given more appealing names, because these are worlds with great potential. Elements such as hydrogen, helium, carbon, and oxygen abound throughout the universe, so we might assume that they are available to such planets, and therefore water would be plentiful. Even worlds completely covered in water are feasible. These basic elements also make up the active ingredients for life. And amino acids are commonplace, so microbial life could emerge on all these target planets quite readily.
Now, we strongly suspect, based on an example of one, our Earth, that the laws of biology work the same everywhere too. And by that I mean the laws that Charles Darwin discovered for us. We think that based on these laws, that evolution can drive life to greater complexity and ultimately to intelligence. It's the smart thing to do.
As with Earth, it could take billions of years for evolution to create ever greater complexity and eventually intelligence. On Earth, Most highly intelligent creatures are of the mammalian family, but the octopus developed its intelligence through an entirely separate route. This would indicate that intelligence has many chances of evolving on these worlds. So, why are there no similar technological societies among these 27 candidate planets? What could be stopping intelligent creatures from developing technology, radios, and spaceships? There are several possible answers. Earth has had major climatic disasters that nearly wiped out life completely. Perhaps a similar disaster was successful on one of these other worlds and killed it. But even with these events befalling some of our candidate planets, there should still be 25 or more potential civilizations.
So, you'd think there'd be plenty of opportunities for life to evolve somewhere else and maybe swing by the Earth, or at least call on the radio. But we haven't found any alien monoliths, or beer cans, or cigarette ends, and we have not heard them tweeting on the radio either. So, where are they? There are lots of theories about that, but I'm going to concentrate on the more plausible ones. First of all, there's the water trap. Maybe the worlds that have water on them are all ocean, for the most part. And if that's the case, you can't discover combustion, you can't make metals, so you can't make a radio or a spaceship. If our dolphin friends lived on an ocean planet, they would be stuck where they are, in the Stone Age, forever. Or maybe on a planet that has dry land but no metals, or very few metals. Same problem, you can't develop a technology. And how about the difficulty of interstellar travel? Maybe it's just too hard. It looks like a real challenge for us. It could be a couple of 100 years before we try that. Maybe it's just too hard. And then there's another theory, which is that we could be the first. We could be the first intelligence to evolve in this part of the galaxy. Someone has to be. We could be the elder race. So here's a time history of Earth. When you look at all the time that life has been here, nearly 4 billion years, humans have only been around for a couple of 100,000 years, civilization for about 6,000 years, depending how you count it, and our technical era only for 200 years. When you look at this picture, it is obvious that the most likely first alien life forms that we discover will not be intelligent. They will be somewhere back here, equivalent to life on Earth during the first 3 billion years of evolution. Similarly, nearby life on an exoplanet is probably plodding its way up the evolutionary ladder. Remember how long it took us to get where we are, where we could even think about life elsewhere.
We Earthlings have the prime real estate in our solar system. We may well be alone for the moment in our section of the galaxy, the only ones with space travel. If so, we need to take care of our planet and our civilization, and stick around long enough to see other intelligences and civilizations emerge over the coming millions of years on those 25 nearby planets.
Asteroids, remnants from the birth of our solar system. From planetoid-sized monsters down to tiny pebbles, they have orbited our sun for billions of years. We have seen some up close, even touched their surface. We count their numbers, chart their courses, and keep a wary eye on these mountains in the dark. Several spacecraft have ventured out towards these rocky worlds. Some have touched down and taken samples with surprising results, then returned them to Earth. Scientists have found these remnants to be complex and full of secrets. There are different types of asteroids, and 2 new robotic probes are ready to study some of these unique targets. One is called Psyche, and it is perhaps one of the most interesting.
Psyche is an asteroid that orbits the sun out between Mars and Jupiter. It's called Psyche because it was the 16th asteroid discovered, and they were all being named after gods and goddesses at that time.
So the Psyche mission is going to visit an asteroid which is called Psyche. And it is a large metal asteroid, a unique body in the solar system, 150 miles in diameter approximately, and made of 40 to 60% iron nickel metal. That makes it a unique body in the solar system. We visited worlds made of ice and worlds made of rock and worlds made of gas before, but we've never visited a metal world. So we'll get to see something unique and different for the first time.
All the rocky planets that we know of, the Earth, Mercury, Venus, Mars, and the Moon, all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field, which may be tied to holding onto our atmosphere and making our planet habitable. There's a lot of study that's going on to understand that. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there. And so Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And so we hope to learn something about what's inside the Earth and other rocky planets by visiting Psyche. But it also tells us about the processes in the very beginning of the solar system. It helps us understand how planets form in the first place.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma-ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma-ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma-ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the Messenger instrument.
That technology that we developed for the Messenger spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can, take what we learned from the prior missions and implement it now and make an even better instrument.
Only one body like this that's this big and made of metal in the solar system. So the big mystery is, where did it come from? How was it created? One of the theories about it is that it was once the inside of a forming planet, because the planets that we know, Earth, Mars, Venus, Jupiter, have metal cores inside of them. So this may have been the metal core that was forming inside of a baby planet, which then collided with other planets that stripped off, forming planets that stripped off that rocky mantle, just leaving a piece of that core in space. And if that's the case, then by studying this body, we'll be able to study the cores of planets like our own, the Earth, in a way that we can never do otherwise.
Psyche is a larger asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber and use it as a target for our input experiment. And we were shooting quartz bead at high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great detail. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place, and this is because the metal is much harder than rocks, and so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data, and there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
There is nothing like the experience of sitting on console on launch day and hearing all the people go around and say, we're go for launch, and then finally getting to say yourself, we are go for launch. It's the culmination of all those years of effort and all those hundreds of people working, and so it's super exciting when you actually, finally say, we're go, and we're gonna get that beast into space. We're going to go launch and do a Mars gravity assist, go by this planet Mars, and then continue on to the asteroid using electric propulsion.
I think no matter what we think it is right now and how much we hypothesize what it might look like, I think it's going to really surprise us and change our views about our solar system when we get there. And that's it's an incredible opportunity to be a part of the team making that happen.
The Psyche mission has suffered several launch delays. However, it should be underway in the next year or two.
Three, 2, 1, 0. Liftoff. Atlas V takes flight.
Another ambitious mission that has launched is Lucy, to study several asteroid targets.
Tower clear.
So Lucy is going to survey 8 asteroids over a 12-year mission life. The first asteroid is in the main belt asteroids. It's Donald Johanson. And then the remaining asteroids are the ones that we call the Trojans. And because we believe that they are remnants of our solar system, by studying their geology, as well as their composition and their mass, then that will give us insight into planets, planet formations, and in particular the outer planets.
The Trojan asteroids, which are located in these Goldilocks zones of gravity-stable orbits in between the Sun and Jupiter, are really leftover fossils from the formation of the solar system. And these fossils are around 4 billion years old, and when the solar system was forming, they were brought into these locations. And the Trojan asteroids, which have been there since the formation of the solar system, are these last unexplored remnants from the cosmic neighborhood creation. And we're extremely excited to go and visit them because of our total lack of understanding of exactly what is out there. And so it's going to be extremely exciting when the Lucy spacecraft explores them.
Some of the most important planetary science questions we're trying to answer are focused on the origin and the evolution of the solar system. Asteroids and other small bodies are really important keys to understanding that history. Amazingly, many of these mysterious worlds have been altered very little in the 4.6 billion years since they first formed. Their relatively pristine state makes comets, asteroids, and some meteorites wonderful storytellers that have preserved clues they can share with us about conditions in the early solar system. In particular, by studying the Trojan asteroids, we can gain more insight into the history of the outer solar system and the giant planets, Jupiter, Saturn, Uranus, and Neptune. We actually find asteroids across the solar system, including near-Earth asteroids that are in orbits that periodically bring them close to Earth, main belt asteroids that orbit the Sun between Mars and Jupiter, the Trojans that Lucy will explore, and the Kuiper Belt just beyond Pluto, which contains some of the most primitive objects in our solar system. Not all of these asteroids are the same, and Lucy is part of a collection of ambitious missions to study the diversity of these asteroid populations that will help us fill in more pieces of that cosmic puzzle.
Lucy will slingshot out from Earth's orbit and pass by the first target, a C-class or carbon-based asteroid named Donald Johanson after the famed archaeologist. Lucy will continue to the orbit of Jupiter and intercept 4 more targets: Eurybates, Orus, Lucas, and Polymele. Some are D&P-class asteroids never seen before and theorized to be rich in volatiles and organics. The probe will then return to Earth for another gravity assist to the trailing Trojans of Jupiter, intercepting the twins Patroclus and Menetius, more P-class objects.
And Lucy spacecraft was named after the Lucy fossil because we will be studying asteroids, which are the fossils of planet formation. But the Lucy spacecraft and the Lucy fossil was named by archaeologist Donald Johanson and his team because apparently when they discovered the hominin, they were listening to the Beatles song Lucy in the Sky with Diamond. Now we do have a diamond. It's our beam splitter, which is on the LTES instrument, which is used to split the beam, is actually made of diamonds.
My job as a mission architect here at Lockheed Martin, it's very interesting, and it sort of encompasses the biggest picture of the mission. What is the trajectory? What sort of propulsion do you need to fly that trajectory? What does the spacecraft look like? So in the case of, for example, Lucy, it's like, okay, it's going out 5 times further from the sun than the Earth is. And so it's going to need big, huge solar arrays just because of that.
Lucy has 3 scientific instruments on board the spacecraft, and we'll also be using 2 of the spacecraft subsystems to contribute to the science investigation. With the LORRI instrument, we'll be able to get panchromatic images, which will tell us about the geology, and the crater history, which gives us the age of the surface. With the TESS instrument, we'll be able to measure the temperature of the surface at different points, and with the RALPH instrument, we'll be able to measure the composition of the surfaces. The Jupiter Trojans, they have a variety of surface characteristics. They have different colors and different surface compositions, and that leads us to believe that maybe they formed somewhere else.
After launch, the Lucy probe failed to lock one of its solar panels in place. Engineers are working on a resolution to this problem.
The Lucy spacecraft will travel 4 billion miles over its mission. And it is a very sophisticated, well-orchestrated trajectory that gets us there.
I cannot wait for those gorgeous images that our instruments are going to take and bring back to Earth. What that's going to tell me and the world is how gorgeous these objects are, what secrets they have to hold, and it's going to start us unlocking these mysteries of the solar system that are out there. I can't wait, and words can't describe just how excited I am to share with everyone these images when they first come back.
This animation is drawn from the recent data release of the ESA Gaia satellite. It reveals the locations of the larger asteroids within our solar system. This tapestry of orbits shows that several near-Earth objects cross our orbital plane. Geological history records that some have hit the Earth with devastating effects.
We've seen asteroids come through the atmosphere and kind of explode and cause some damage. And thankfully, so far, nothing recent enough that it really has a large impact on our civilization, but it could happen.
There are multiple different ways that you might attack the problem of, oh no, doomsday asteroid is inbound. One of those ways is a kinetic interceptor, which is what DART is working on.
As part of planetary defense, DART, which stands for Double Asteroid Redirection Test, its mission is to impact an asteroid in a binary system.
The reason we're doing this test is to try and prove out the technologies that would be needed to, say, save Earth if an asteroid were coming our direction and we needed to adjust its trajectory so that it would miss the planet.
SmartNav is the autonomous algorithm on board, and the purpose of SmartNav is to identify Dimorphos, which is the smaller of the 2 asteroids in the Didymos system, and we send maneuver commands to the spacecraft for the spacecraft to hit Dimorphos.
And we understand where about 40% of those asteroids are. We know that no known asteroid is a danger to the Earth right now. But the concern is about the asteroids we don't know about yet. And if we should ever discover an asteroid that's on a collision course with Earth, we want to be able to discover this years in advance so we can give the asteroid a push, not to destroy it, we probably wouldn't be able to do that anyway, but just to prevent that collision. And the DART mission, the Double Asteroid Redirection Test, is our first test of one way of doing that.
Launched aboard a SpaceX Falcon rocket, DART is well on its way to its target.
So the way an ion thruster works is that it utilizes electrical energy to ionize propellant and accelerate it using electric and magnetic fields. What NEXT does is that it increases the power level, you get more thrust out of it, it's more fuel efficient, it lasts longer, basically kind of improves things in almost every way and makes it very beneficial for end users to utilize.
When they're rolled out and fully deployed, they're almost 10 meters long. This is the last time that anyone will ever see these arrays fully deployed. Once we stow them here at DSS, they will not be deployed again until we're in space on the DART spacecraft. Part of our detailed inspection entails Andrew looking at the cell by cell on these arrays, again, that are almost 10 meters long. He'll look at them at different wavelengths of light, different angles, just to assure ourselves that we've found every anomaly possible in these cells and they're fully characterized with the entire array, and we know exactly what we have and the condition it's in when we launch.
DART's going to a binary asteroid, a double asteroid, for two really good reasons. The little asteroid, Dimorphos, which is in orbit around the big asteroid, Didymos, that asteroid is about the size of object that we would tend to be concerned about. The most abundant asteroids are the small ones, and this one, about 160 meters across, or about the size of a football stadium, is large enough that it really would cause severe damage if it struck the Earth. Now, by doing our experiment, a kinetic impact experiment on the small moonlet asteroid, we're able to measure our effectiveness in deflecting the asteroid by watching the change in the orbit of the little asteroid around the big one. It makes that measurement a lot more precise and a lot easier to do with telescopes on Earth. The other reason we're doing it is that the presence of the large asteroid there keeps the little one in orbit around it as the pair go around the sun. So that means that this asteroid, which is not a danger to Earth now, will never become a danger to the Earth because of anything that we do in the DART mission. DART is carrying a small CubeSat. It's called the Licia Cube. It was contributed by the Italian Space Agency, and its job basically is to watch the impact from a little distance away. It's riding along on the DART spacecraft, and it's going to be deployed a few days before the kinetic impact. It's going to maneuver and offset itself to the side so that it doesn't run into the same asteroid that DART is running into, and it's got two cameras on it that are going to try to first catch the actual impact of DART on camera, but then more importantly, see the ejecta, the plume of material that's blown off the surface of the asteroid and how that develops. If we're fortunate, we'll be able to see the impact crater newly formed by the DART impact. And then, of course, Licia Cube is going to do something that DART can't do, that is fly past the asteroid, look back, and get the full three-dimensional shape of the object that we hit, which we won't know until we actually get there.
One other threat to Earth is the interstellar object passing through our solar system. They arrive without warning, fast-moving and having no known orbit. Another hazardous mountain in the dark. The search for life within our solar system continues unabated. Scientists are following the signs for water, either deep oceans or hot springs where life can evolve. There are exciting candidates to explore: the icy moons of Jupiter, oceans in the sky. Orbiting the giant Jupiter are 3 prime candidates. Ganymede, the largest moon in the solar system. Callisto, once thought to be dead, may harbor a salty ocean. And the active Europa, with its plumes of water erupting into space. The European Space Agency is about to launch a probe to investigate these 3 potential sites. A daring mission called JUICE.
JUICE is the Jupiter Icy Moon Explorer. So it's the first large mission of the Cosmic Vision program of the European Space Agency, and has the objective to study the Jupiter system and 3 of the Galilean moons, 3 icy moons, which are Europa, Ganymede, and Callisto.
This mission is of particular importance for the European industry because this is the first time that Europe is going to Jupiter. So we are supporting the European Space Agency and beyond the European scientific community in their endeavor to go to Jupiter and explore Jupiter and their moons.
The scientific objectives of JUICE are multiple. So first of all, humanity always poses itself a question: are we alone in the universe? Is there life outside Earth? To respond to this question, first we need to answer to another question: are environments where life can be sustained before going and search for life? And this is one of the main objectives for JUICE, to search if on the environment, on the ocean world of Europa and Ganymede, there are the conditions to sustain life. Now, from the past missions, we know that some of these conditions are fulfilled, and we want to go with JUICE to investigate even deeper and to make sure that these conditions are there. And these conditions are, for example, there is water, there is liquid water, there is a source of energy inside the planets, so there is energy. There are the chemical compounds which are needed to sustain life, the life as we know, so based on carbon. And is a protected, is a stable environment because it's under the crust of the moons. So once these 4 elements are fulfilled, there is the probability that life will be sustained outside Earth is very high. The other objective of JUICE is to study the Jupiter system in its integrality, as seen as a miniaturized solar system, if you want. We have a gas giant with bodies that go around this body, and studying the interaction of the gas giant with these bodies, we can understand better, for example, the development of our solar system, how it was born, how it works, and etc.
So JUICE is a very exciting mission. So we are going to explore Jupiter in details. And in particular, I would like to know whether there are conditions hospitable for life around a gas giant like Jupiter, and we are going to focus that on the 3 icy moons, which are Europa, Ganymede, and Callisto. And we would like to know whether inside those moons there are conditions which are interesting for life, and we are going in particular to explore the liquid water which are underneath the crust of those moons.
In the past, there were other missions that they analyzed the Jupiter system, like Galileo, for example, has given us important information to build the JUICE mission. There is also Cassini that passed by, that we gather a lot of data also from it, and also from observation from Earth, also observation from Hubble, for example, has provided us loads of data which are precious to build JUICE and to build also the profile of the mission, to know what we are going to study.
We have in total 10 scientific instruments on JUICE. And basically we will observe Jupiter and its moons in all possible wavelengths and type of observations that we can do. So we have a number of telescopes in all wavelengths, visible, infrared, ultraviolet. We have a radiometer to sense the atmosphere, the structure of winds of Jupiter and their moons. And we have electric and magnetic sensors. Some of them will be deployed at the tip of a magnetometer boom. So RIME is this big antenna that you see there, deployed just behind us. It is a radar antenna that is working at a very low wavelength, 9 megahertz. So for that to happen, you need a very long piece of antenna that will be able to sound very deep below the surface, the internal structure of the moons, in particular Europa, Callisto and Ganymede. The objective is to try and locate the liquid water ocean that is underneath the icy crust of these moons. As of today, we are still not sure how deep we have to dig, let's say, to find this ocean, and this antenna will help us figure out at which depth we can find this ocean.
At the moment, the nominal science is foreseen to last 4 years. In these 4 years, Jupiter will make all the investigation. It will make some flybys of Europa, flybys of Callisto, and then we'll go into the details of the analysis of Ganymede. We'll stay in orbit around Ganymede for a good part of the Jupiter tour.
JUICE will start its science mission about 6 months prior to entering orbit around Jupiter, making observations as it approaches its destination. Once in the Jovian system, a gravity-assist flyby of Jupiter's largest moon, Ganymede, also the largest moon in the solar system, will help JUICE enter orbit around the gas giant. During its operations, the probe will make 2 flybys of Europa in July 2032. Europa has the strongest evidence of an ocean of liquid water under its icy shell. JUICE will study the moon's active zones, surface composition, geology, and the plasma environment around the moon. A sequence of Callisto flybys will then be used to study this ancient cratered world that may also harbour a subsurface ocean, but will also change the angle of JUICE's orbit, making it possible to investigate the polar regions of Jupiter. Now that the probe is fully assembled, it has to be thoroughly flight tested to ensure its survivability, because the giant's magnetosphere traps an intense and dangerous radiation environment.
This milestone is very important because here we have the spacecraft. It's integrated, it's ready. We have all the 10 instruments are delivered, are there. All the platform units are there, the antennas is all in place. So the spacecraft is ready for the test campaign to verify finally that everything's worked as expected within the performances they were expecting. And this is 1 year from launch. So this is a very important milestone. The spacecraft integrated is there, and we can carry on with the test phase.
So we start first with electromagnetic compatibility test. The goal is to verify that the spacecraft has a sufficiently low level of electromagnetic perturbations, because a number of instruments of JUICE will sense electric and magnetic fields at Jupiter, and we do not want the spacecraft to be a source of perturbation for that. After that, we will do a number of mechanical tests. It will be done over summer. Here the goal is to verify that the spacecraft can survive the launch environment that will be imposed by Ariane 5 when we will launch to Jupiter.
It is true that the JUICE spacecraft that we can see on the background is going to be launched in space, meaning that it's not like for aircraft. We can repair something after a couple of hours of working. We need to make sure that before we launch, everything will work properly as expected.
And then there will be additional tests, like a vibration test, including with the solar array, so that will be quite exciting. We have also what we call EMC test, so to make sure that the spacecraft is quiet from the electromagnetic point of view. It's very important for the science of the mission. And additional tests like a communication between the spacecraft and the ESOC flight control team that we need to control the spacecraft once it flies. So all these tests will take place in the coming 10 months. And after that, hopefully the spacecraft will be declared ready for launch, and we will ship the spacecraft to its final destination on Earth, which is the French Guiana spaceport.
Replicating the environs of space is no easy task here on Earth. At ESA's test center, ESTEC, in the Netherlands, is the Large Space Simulator, which can model the vacuum of space and simulate both the extreme heat and cold of deep space. It is Europe's largest vacuum chamber, and its internal black panels, which are filled with liquid nitrogen, were used to cool the environment down to around minus 180 degrees Celsius. To test against extreme heat, lamps are used to raise the temperature up to 250 degrees Celsius.
JUICE, in order to fly to Jupiter, will do some gravity assist around several planets, among them the Earth and Venus, which is very close to the Sun. And in fact, all the electronics inside the spacecraft are supposed to work properly in a certain range of temperature, and the thermal design of the JUICE spacecraft aims at protecting this unit from the very harsh environment, cold or hot, for this unit, in order for them to work properly when we will start to do science at the Jupiter azimuths.
To reproduce the heat side of space, so when we go close to the sun, we simulate the sun. And in order to do so, we have a set of lamps, very powerful lamps that are reflected in 121 mirrors that can be reconfigured depending on the mission characteristics. And in this case, we simulate the heat of the sun while the spacecraft goes through Venus. Why Venus? Because the JUICE mission is doing a flyby in Venus before going finally to Jupiter.
Yeah, so when I saw JUICE going to the space simulator, I had a mixed feeling, of course, because it was a very scary moment. It's a little bit like your baby spacecraft, so you're a bit scared that something will go wrong. But at the same time, you know that the team, in particular, the test center people, they know what they are doing, so it's quite a secure activity. So it was a mixed feeling, but you always feel nervous when you see the spacecraft going into the large space simulator.
And in addition to that, we have also some requirements coming from the environment itself of Jupiter, like temperature and radiation. Jupiter is a very aggressive radiation environment that is making the whole design of a spacecraft even more complex.
Jupiter has the largest magnetosphere in the solar system, 18,000 times more powerful than Earth's. In combination with the sulfur dioxide ejected by the Moon, the space around Jupiter is loaded with plasma. The magnetosphere also traps and accelerates particles, forming an intense radiation field that is thousands of times more powerful than Earth's Van Allen belt. The result is a very hazardous environment for spacecraft and potentially humans.
After that, we will also test the propulsion system in order to be sure that it is leak-tight and fully operational when placed into a flight configuration. We will do a second thermal vacuum test in a chamber very close to this facility in October in order to verify in pressure and temperature conditions and full flight configuration that the spacecraft is behaving nominally in all functions. And finally, after having tested the spacecraft in all these various environments, we will verify a last time that from a functional perspective, the spacecraft behaves nominally and is ready for shipment to the launch site.
That launch site is Europe's spaceport in Kourou in French Guiana, where the venerable Ariane 5 will lift JUICE into space. It will also be the final launch of the Ariane 5 rocket series, one of the most reliable launch systems, with 112 launches and just 5 partial or complete failures. The Ariane 5 heavy lift vehicle has launched many of the most important space probes, including the Rosetta mission and most recently the Webb Space Telescope. It will be replaced by the Ariane 6 heavy lift booster.
JUICE will be launched next year in 2023 in April, the beginning of April. The launch window will open on the 5th of April and will stay open for about 3 weeks because of celestial mechanics. And then the spacecraft will, before being injected into the transfer orbit to Jupiter, will have to acquire more speed, and we will need to do a certain amount of gravity assist to the inner planets of the solar system. We'll do a gravity assist, which will be a first, which will be a Moon, Earth gravity assist. Then there will be a Venus gravity assist, other 2 flybys of Earth, and then we'll be projected to the insertion orbit to Jupiter for other 2 years. So overall, it will take about 8 years to get to Jupiter.
The gravity assists, 25 in total, will allow the probe to gain the necessary speed to reach its final destinations without consuming the 3,000 kilograms of precious fuel reserved for course corrections and orbital insertions. JUICE will arrive at Jupiter in 2031, followed by a proposed orbital insertion around Ganymede in 2034, all part of the European Cosmic Vision Programme.
The Cosmic Vision Programme has an objective of studying also outer worlds, so it will be complementary to future missions, to mission currently in development, like Plato, like Ariel, like SMILE, and be complementary with the future missions. There will be an Envision for the study of Venus, with Athena, for example, for the study of the universe, with LISA for the study of the gravitational waves. So it will be complementary to have a full and round information on astronomy and planetary science. And it will be also part of the inspiration that the Cosmic Vision Programme wants to transmit to the scientific community and to the public. So JUICE has been developed by a huge industrial consortium to build the spacecraft itself. So in particular, we have Airbus France, which is the main contractor to build the spacecraft, and which is made 95% by European companies. It's about over 100 companies from Europe, and about the 5% of contribution from United States. The JUICE embarks 10 scientific payloads, and the payloads are the contribution from leading funding agency, which are the space agencies. So in particular, we have CNES, there is the Italian Space Agency, DLR, German Space Agency, there is the UK Space Agency, Swedish Space Agency, and we have also contribution on an instrument, another contribution from NASA. as well as from JAXA, and also from the Israeli Space Agency. And each of these scientific consortium is built by other institutions from as well over Europe. So we have also contribution from Austria, from Belgium, from is a European wide consortium.
Over time, JUICE's orbit around Ganymede will naturally decay. Eventually, there will not be enough propellant to maintain it, and it will make a grazing impact onto the surface in late 2035. JUICE will not be alone in its mission. NASA is also launching a probe to the same local. However, its primary goal will be to study Europa exclusively. The mission is the Europa Clipper. Due for launch 2 years after JUICE, the Europa Clipper will ride a SpaceX Falcon Heavy. This time, the probe will utilize Mars for a gravity assist in 2025, then Earth a year later, arriving in the Jovian system in 2030, a year ahead of JUICE. Due to the harsh radiation environment, the Clipper will not orbit Europa, but instead orbit Jupiter and make multiple passes of Europa, 44 encounters over 3.5 years. Utilizing the other Jovian moons for gravity assists the Clipper, which will adjust its orbit to pass by Europa and various altitudes from 2,700 kilometers to a mere 25 kilometers, where it will be able to pass through the water plumes erupting from the surface. It will carry 9 instruments, including thermal and radar imaging, ultraviolet spectroscopy, and surface dust analyzer.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Because once we have investigated whether life can be sustained in the icy moons in Europa or Ganymede, then there could be other missions that will go to analyze more in depth if life is really there, maybe with penetrators, with rovers, with sample return missions. And one of the objective also of cosmic vision is to be an inspirator for future missions. Also for a sample return, for example, why not on the icy moons of Jupiter?
It is one of the most complex and sophisticated scientific instruments ever built. It is orbiting our Sun 1 million kilometers out in space in temperatures of -266 degrees Celsius. It is a time machine that will peer deep into the past and reveal unexplored reaches. And it will be our key to understanding where we fit in this enormous universe. Launched aboard an Ariane 5 rocket, the James Webb Telescope has successfully reached its destination, unfurled, and begun its great adventure.
Hubble revolutionized astronomy. Hubble showed us the early universe. Hubble showed us what the universe works like. And as these revolutionary findings came along, people realized we need a next generation space telescope. This was 25 years ago. And this is how Webb came into being. Now, you can see 25 years of development time. This is not unusual for a large space mission, from the first idea to fruition, to the launch. And this is why these missions are really once-in-a-generation launches. We are witnessing something particularly special that an astronomer typically gets to witness once, if they are lucky, twice in their entire career.
James Webb Space Telescope is a collaboration between NASA, ESA, and the Canadian Space Agency. So altogether, that's 24 countries, lots of industrial companies, academic institutions, universities, and thousands of scientists across the whole world are now waiting to use the telescope. So by combining the power of the best in engineering and science from all of those countries in this international collaboration, we can do much more together than we could do on our own.
The origin of Webb is the search for our origins. We want to find out where the first galaxies formed, how they formed, when they started making their stars in the very early universe not long after the Big Bang. And to do this, Webb uses its big mirror and its infrared vision to look into these really early days, observe the light from these galaxies that's been traveling to us for billions of years, and it shows us these galaxies how they were billions of years ago.
Sure, so infrared is a longer wavelength than visible light. So we can't see infrared, but James Webb can. And what's important about an infrared telescope is it allows us to see through clouds of gas and dust and see the planets and stars and galaxies that are beyond. In addition, James Webb has a larger mirror than Hubble, so it can see back further in time, and it's orbiting at a different point.
James Webb is very complementary to everything that has been done before, to Hubble, to Herschel, but will be a huge step forward just because the collective area is huge. 6.5 meter is pretty impressive. Hubble, as a comparison, was 2.4. So we're talking of a collective area which is much bigger, much more sensitivity. We say 100 times more sensitive. With a complement of state-of-the-art instruments which will take images and spectra in wavelength regimes that we haven't explored as much from space up to now.
The telescope houses 4 scientific packages: MIRI, a mid-infrared instrument, the near-infrared NIRCam, NIRSpec, a spectrographic analyzer, and the NIRIS imager and guidance sensor.
The near-infrared spectrograph, or NIRSpec, it's one of the 4 scientific instruments that we fly on James Webb Space Telescope, or Webb Telescope. It's very important because it will allow us to analyze the light of the astronomical objects we will observe. A spectrograph works very much like a prism. In fact, there's a prism inside our instrument and gratings, and they, like the prism, splits the white light into its rainbow colors. These instruments will split the near-infrared lights from the astronomical object into its components. And this is very useful to scientists because from that they can understand the physics of the objects they are observing, what are the temperature, the elements, the physical condition, and therefore we can understand what's going on the objects we observe. So we will observe all sorts of astronomical objects, from galaxies, and the focus is very much on very far away galaxies that are 13 billion light years away from us, so back in the far past, that they were forming soon after the Big Bang, from very what we call nearby objects, which are not really nearby, but they are exoplanets in stars around our neighborhood, the neighborhood of the solar systems in our galaxy. So this is the type of objects we will observe and investigations, it's about understanding what are the atmospheric condition on the exoplanets or what are the physical condition of the galaxies we observe far away. So going back to the very far away galaxies, this instrument NIRSPEC will play a crucial role in observing this far away galaxy and telling us what is the physics. So again, what are elements are present, in which proportion, what are the temperature, and that is fundamental if you want to understand how galaxies form, which is one of the big questions we have in astronomy. We see trillions of galaxies around us, how all these galaxies formed. And with this instrument we can piece together more of the puzzle. It complements the other instrument because of its function of a spectrograph. So on the Webb telescope we have cameras, other type of spectrograph, one particular MIRI, which is also a partially European instrument, which will focus on the mid-infrared light. Near-infrared is the focus of NIRSPEC. Analyzing the light that comes from astronomical objects in the near-infrared wavelength range. While with the camera we see images, so we detect the objects and we know where they are and what are the main characteristics. With NIRSPEC we focus really on certain objects and analyze the lights and split the lights into its components, and with that understand the physics of the objects we are observing.
The telescope is in a halo orbit at the L2 or second Lagrange point and is orientated away from our Sun, with the sun shield keeping the instruments at their very low operating temperatures.
Where is the telescope pointing relative to the spacecraft? So we waited for the near-infrared camera to get the detectors cold enough so that we could take images, and we did some evaluation of that. And once we were convinced that it could take images, we were really trying to determine if we pointed at a bright isolated star, where's the telescope pointing? So we picked a star that was very bright and didn't have any stars near it that would contaminate the image. We know that the primary mirror segments aren't aligned yet, so they actually act like 18 separate telescopes, and we expect to see 18 separate images, one for each mirror, that are a little bit blurry at this point because we haven't aligned or focused anything. And so we pointed at a bright star and we made a mosaic. We actually took the near-infrared camera and we took images in different parts of the sky, and then we looked for the 18 spots from the 18 different telescopes, if you will, and we were very excited to find them. They were actually very close to where we were pointing, well within our expected size of where they might land. And the 18 spots were actually fairly close to each other as well. So really everything was very close to what was predicted and much better than what we considered to be the worst case pointing. So we were really excited about that.
Over the following months, each individual mirror was adjusted and focused, then aligned together to create one single image. The alignment image of the single bright star gave an indication of the power of the Webb telescope. As seen here, behind the bright star, the image captured numerous distant galaxies. The science team then captured several sample images of different objects.
The first images from the James Webb Space Telescope are designed to demonstrate the full range of the capabilities of the telescope.
Scientists then sat down and studied these many test images, which amazed the team.
The cluster is, it's probably bigger than that. There's lots of light. Yeah. But I think when you stretch the background, I didn't dare to say. You should have said it. Yeah. This is Iraq. It's going from the 70s to the 80s and 90s. Even in your camera, it's
really stays the same in all wavelengths.
We're seeing a sample of the amazing science that Webb will be able to do over the coming years. Remember, it's just a sample. So we are seeing scenes and vistas from across the universe, toward the first galaxies, to stellar birth and stellar death. And we're seeing an exoplanet spectrum for the first time with Webb, showing water or steam in its atmosphere. So here, what we're seeing in this deep field image, Webb's first deep field, is a massive cluster of galaxies. And what this cluster does is it bends the light from even more distant galaxies coming behind it. And you can see that as sort of bananas or streaks in the field. And this field allows us to look for some of the very first luminous structures in the universe, the first stars and galaxies, and this was one of the reasons that Webb was originally built. So with the Southern Ring Nebula, the image here, what you see is a star that is similar to our own sun, but 5 billion years in the future when it dies. And so when stars like that die, they push off the outer atmospheres, and this gas cloud you see is filled with elements like carbon and oxygen, kind of elements that we are made of. And this is how dying stars seed the galaxy with these elements that ultimately are important for the formation of life. So here we are seeing a small group of galaxies that what we call interact, they're actually colliding with each other. And this is a very fundamental part in the evolution of galaxies. They bump into each other all the time. And when they bump into each other, they create shock waves. And in these shock waves, you have this tremendous formation of new stars. And you see these shock waves in this image here, and you see the formation of stars there.
Yes, this is a set of galaxies that are sort of locked in a cosmic dance, and so they're moving, and two of them are merging, and we can see all of them moving around in that, and their interactions.
You also see the galaxies superimposed on this field of distant galaxies in the background, whose light has probably traveled through the universe for billions of years. And so this is very typical for Webb images, that everywhere we look, we're going to have these distant galaxies in the background.
And one of the main things that we want to look at with the James Webb Space Telescope is the most distant galaxies in our universe, the furthest objects away. And that also means that they were the first objects to form after the Big Bang, the first stars and galaxies about 13.5 billion years ago. The reason that all of their light is now in the infrared is because the universe is expanding. And as it expands, the light from those most distant objects gets redshifted to infrared wavelengths. So again, Hubble can't see them, but the James Webb Space Telescope is designed exactly to see these very distant, very faint objects.
Those emission lines, yeah.
Oh yeah, this is such a beautiful image, and maybe my favorite. What we see here is a stellar nursery, a cloud of gas and dust that is actively forming new stars. And you see this as sort of a landscape that looks like mountains because the cloud is being eroded away by hot stars that's off the field to the top. And they're cooking off the cloud, and as they do that, they push on it. And so what that means is that you can form new stars sort of close to the surface of the cloud there, and you can see those stars popping out, and you can see them also create jets and outflows as part of this process that move through the cloud and create these streaky structures in it.
In comparison, the Hubble imagery here captures the visible light. Now, compared to the Webb images, you can see the dark dust turn transparent, revealing what is within and behind the veil.
I'm really excited about James Webb and the spectroscopic capabilities. It's absolutely revolutionary, the sensitivity and the resolution we can get to look at the dust and the forming stars in some of the very most distant galaxies to us, where we can actually see individual stars and work out what the chemical compositions they're producing in terms of dust and the minerals they're producing and the life cycle of matter in the universe, that chemical evolution of galaxies. And no other instrument, no ground-based instrument can do this because of the atmosphere. Only space-based instruments can do this. And previously, the previous generations have been so small, they've been able to only look at galaxies in the Milky Way or in the Magellanic Clouds. But James Webb will be able to push that envelope out to lots of galaxies in the local group, and so we can look at very different formation scenarios towards the early universe. So that's what I'm most excited about, is these dying stars and forming stars.
The hope is Webb will be able to see so far back in time, it will reveal the very first galaxies and stars created after the Big Bang.
Lots of big questions. How do galaxies evolve? So the Hubble Deep Field has given us some hints of what we think is happening, but we haven't been able to see it in enough detail or with enough galaxies to really know. So it's going to fill in, almost you could think of it as a gap in time between the Big Bang and the galaxies we can study with Hubble, and we'll find galaxies that are in that gap.
This image is of the spiral galaxy IC 5332, which is over 29 million light-years away. The infrared web sees through like an X-ray into the interior structure of the galaxy.
Well, it's going to allow us to understand every phase of cosmic history for the last 13.5 billion years. So we'll be able to answer questions like, how are galaxies formed and where do we fit into the cosmos? We'll be able to see the formation of stars and planets. We'll also be able to understand atmospheres of exoplanets.
The James Webb also captured images of local residents in our own solar system. Here is Jupiter seen in the near-infrared. It reveals the polar auroras and the heat signatures deep within the clouds of our largest neighbor. Here is Neptune as never seen before, its rings clearly visible along with several of its moons. The most prominent features of Neptune's atmosphere in this image are a series of bright patches in the planet's southern hemisphere that represent high-altitude methane ice clouds. More subtly, a thin line of brightness circling the planet's equator could be a visual signature of global atmospheric circulation that powers Neptune's winds and storms.
I think the great thing about Webb is that it actually touches all of astronomy. So because it's so flexible, you can use it to study things inside our own solar system, but you can also use it to find examples of the very first galaxies. So it really is spanning almost the entire history of the universe. So it's really going to be transformative to lots of different areas. I think the two areas that are going to be transformed the most are my own field, which is finding and understanding these very early galaxies, and then on the other end of the scale, actually looking at planets around other stars that are relatively nearby to us. But I think every single astronomer in the world will ultimately be taking some of the results from Webb and incorporating it into their own research.
Astronomers have made giant steps in our understanding of the universe over the past decades, but there remains much to learn about our cosmic origins, and the range of questions waiting to be answered is causing high expectations.
Webb is more than tens of thousands of scientists. Webb is 8 billion people looking for the origins.
Black holes, where time and space converge under gravity's immutable power. These extremes of nature, once considered improbable, are now giving up their secrets. In fact, scientists have been able to imagine the impossible, the black hole at the center of our galaxy. We can now peer into the abyss. The concept of black holes was first proposed by the German astronomer and physicist Karl Schwarzschild, barely a year after Albert Einstein had published his works on the field equations of gravitation in 1915. Schwarzschild wrote to Einstein from the German trenches of the First World War, detailing his mathematical results of his gravitational equations. Sadly, the brilliant scientist later succumbed to a skin disease he contracted in the trenches at the age of 42. The existence of these so-called frozen stars was written about and debated for 50 years. In 1967, physicist John Wheeler coined the term black hole to describe these impossible objects and the conditions that would create them. New Zealander Roy Kerr advanced the concept by publishing a solution to the equations, which would require that black holes spin like all other astronomical bodies. Then Stephen Hawking and Roger Penrose theorized that black holes could emit radiation, now called Hawking radiation. The theory: if a black hole had no material to absorb and grow, then a black hole could evaporate, effectively shrink and die. All scientists had to do was find one to study. Quasars, the tremendously bright, distant objects, were factored in as a strong case for black hole accretion, the only imaginable energy source capable of such incredible luminosity. In 1964, astronomers discovered one of the brightest X-ray sources in the sky in the constellation Cygnus, and labelled Cygnus X1. The powerful source didn't coincide with any bright optical or radio source, leaving it in the mystery basket of observations. Before long, with advancements in computers and space-based telescopes like Hubble, black holes were eventually detected, or their effect on their surrounds were detected, as black holes by their nature can't be seen.
Black holes are these incredibly fascinating but mysterious objects. We know they sit at the hearts of galaxies, and they drive how those galaxies grow and how those galaxies die. They swallow gas and stars up. There are also these incredibly enigmatic and mysterious objects that live at the boundary between our two great theories of physics: general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
Black holes are literally gravity run amok. They are purely gravitational objects predicted by Einstein's theory of general relativity, and their most notable and terrifying feature is that things go in and they never come back out.
Wonder comes to my mind first. Such objects were never expected to exist in nature until very recently. As a matter of fact, I was a complete skeptic about black holes as recently as 20 years ago.
Black holes are places where Einstein's theory of general relativity is the whole story, not merely a perturbation on top of Newton's theory, which explains the dynamics of planets in our solar system. As a result, black holes provide a unique environment in which to probe general relativity specifically and strong gravity generally, and its implications across the cosmos.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, it also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
If you like Einstein's theory of gravity, then black holes are, one of the most interesting examples of this theory. And this is my role within this project. I am a theorist. I work with equations and simulations, and my role is that to try and understand whether the image that we produce corresponds to the predictions of Einstein's theory or maybe to something else.
From the physics side, I find that more an interesting question, that this is basically some kind of rent or tear maybe in space-time, and a place where we don't understand the physics and have a lot of serious questions about information theory.
I was very excited the first time I saw the first image. For a long time, this was purely theoretical. We were predicting that we would see certain features in the image, but we didn't really know, was it really there? And now we know, and it was exciting that all of that uncertainty collapsed in that moment.
So as the magnetized gas is falling onto the black hole, it heats up and therefore generates the light that we then see. Now, from our daily experience, we expect that light travels on straight paths and straight trajectories. We call them rays. Here, the situation is very different. We have a black hole sitting right there. So what the black hole is doing, it is deflecting and bending the light rays away from the straight paths that we understand in our daily life. And in fact, it can be so strong that we can see things that are behind the black hole that we thought are obstructed by it, just because the black hole is bending the light rays into our line of sight.
Scientists began running simulations on supercomputers. Multiple computational models were visualized to better understand what they might find in the data collected from their observations.
After we computed the radiative signature of our simulations, we have to compare them to the observations. And this can be imagined as you are in a stadium during a football match, and you have an image. And you want to figure out if this person or whatever is on this image is among the spectators in the stadium. So what you do is you take this image and try to match it with all the 60,000 spectators in the stadium. And you do this while you rotate it, you scale it, you increase the contrast, and you try to figure out first what is on your image. Is it a person, is it a cat or whatever? And try to match this to the spectators. And this seems trivial, but it's not. It's a highly computational, demanding process. So we need a supercomputer, which we have in Frankfurt. And we developed a so-called genetic algorithm, which is a very smart way running through these images and try to adjust them. And this takes roughly a month. And after this calculation time, we have maybe 10 of those spectators which match your image. And this is very similar to what we do in the EHT. So we try to compare and match our observations with the theoretical predictions.
So what is most surprising of this experience is that we managed to get a very good image the first time we tried to synchronize all of these telescopes at the same time. It is not so surprising that we obtained the image that we had predicted through simulations because, well, we believe our simulations are correct and because we believe that the theory of Einstein's general relativity is the correct one.
In 2019, they achieved their result, an image of the shadow of a massive black hole in the distant M87 galaxy. It was a world-first achievement celebrated around the globe.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region, and you know immediately we are looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
We wanted to take an image of a black hole, and the problem with black holes is that they are very small. So you want to take a very big black hole, which unfortunately is very far away from us. And so you need a big telescope. This telescope is 100 meters in diameter, but it's not enough. You want a bigger telescope, and of course it's impossible to build, but you can create a virtual telescope by joining different telescopes in different locations, and so you can build a telescope which is as big as the Earth. And in fact, that's exactly what we've done. We joined telescope like this with telescope on the United States, and one even in the South Pole, to get a very sharp image. Actually, an image that is comparable to seeing an orange on the moon. Black holes tell you that there are regions inside them that cannot be explored. And for a physicist, this is very disturbing and attractive at the same time, because we don't like to have doors which we cannot cross. And in particular, inside black holes, physics is even expected to fail completely. And so this even adds fascination to these objects.
The future of the project will hopefully going towards a new understanding of more fundamental questions in physics. If this is true that black holes are the extreme objects where we can study gravity, and we know that general relativity, which describes black holes in the outer part up to the event horizon, breaks down at the event horizon. So the big hope is that with more data we might be able to study the physics beyond general relativity. So maybe there might be quantum physics ruling beyond the event horizon, or the combination of quantum physics and general relativity, which would be the theory of quantum gravity, which is non-existent at the moment, but we might learn more about this with the help of studying black holes.
Our experiments are like an Arctic expedition. We have to plan for months and months and months in advance, gather our equipment, and then we have this great migration of people to observatories all around the world. We stay up all night, we run our telescopes, and then we have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
Data analysis, imaging black holes, and doing simulations is very exciting. It's also very difficult and requires a lot of patience. It's a very long process, but seeing the final product is very satisfying.
The Event Horizon Telescope collaboration is this amazing group of fantastic people from all around the world. Americans, Europeans, people from Asia, who've come together with all their technical expertise and scientific expertise to make this image of a ring around the black hole. The future of this project is amazing because now that we've seen what we're after, we have so many more questions to ask about it, to push into the regime of, can we decide, is Einstein right? Can we study how gas really gets swallowed by the black hole? Can we see a giant eruption of radiation, of particles coming out of the system? So many things to do. We've really only just begun.
Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It was a fantastic way of combining talents from different people in a way that otherwise would have not been possible. In order to take this picture, you need the cooperation, the simultaneous observations of many radio telescopes across the planet. You need to have the largest possible network of telescopes taking the same image at the same time.
New goals for the Event Horizon Telescope were quickly set. The M87 massive black hole is far away from Earth. Scientists wanted to get a closer look and decided to image another black hole at the center of a galaxy, one much closer, but also much smaller and shrouded in gas and dust.
So if you try to look into the center of galaxies, it's usually blocked from view by dust and other stuff. In the radio, you can look through, like here today, we can look through rain, you can look through clouds, and so we can look through dust. And with combining radio telescope like this together with other telescopes in the world, you can peer right into the center of the galaxy and see this black hole.
The science result is just one point in time in the project, and we are always learning more about how the instrument works, how people work, how new theories come about, and so this is an evolution in my perspective. It's not just one point in time where you say, this is it, that's done. It always continues.
So we still have a lot of mysteries to be solved, problems to be tackled. There are still many questions about black holes, so I would like to study further the black holes.
The Event Horizon Telescope targeted the black hole in Sagittarius A, which is the location of the center of our very own Milky Way galaxy.
The long-term future of experiments like the Event Horizon Telescope is moving this kind of instrument into space and starting imaging black holes from space, which improves a lot this kind of observation because it allows us to have even higher angular resolution than what we have now. So we will be able, maybe in 20 years, 30 years, make a very accurate images of the event horizon of a black hole.
Not only did scientists image the black hole, they sampled the radio emissions from the surrounding hot gases, giving us an audio impression, the sounds of a black hole.
So far, we've been looking at the closest massive black hole, but quasars, very distant from us, with gravity, we can see the motion of gas and resolve the sizes of these regions and thereby measure then the mass precisely. So if you can do this for many quasars, many distant objects, then you can solve perhaps the riddle how massive black holes played a role in the evolution of galaxies. We now know that basically every galaxy has at its center a massive black hole of different masses. We'd like to understand that in detail. There is, if you like, a symbiosis between these black holes and galaxies, and we need to understand that in order to understand the evolution of the universe.
Studying the data from the Event Horizon Telescope continues to reveal more detail. In this case, X-ray emissions reveal magnetic lines of force through the orbiting gas clouds. Further study of the X-ray emissions is currently underway with a new space-based X-ray observatory, the Imaging X-ray Polarimetry Explorer, or XP. Launched in 2021, XP is designed to observe extreme cosmic objects like pulsars, neutron stars, and black holes. This satellite is able to study X-ray radiation, which is polarized or oscillating in a particular direction. This reveals more detail of the physics of these high-temperature environments, particularly around black holes.
But there are two other parameters that we could look at if we only had the tools to do that, and those have to do with the polarization, the degree of polarization, and the position angle, the angle associated with the polarization. So by doing this mission, we're opening up 2 more degrees of freedom to be able to try to understand how are the X-rays produced, what are the models. We have to be able to predict the polarization that we will turn out to measure. So it's really exciting. Our science working group has studied we have 7 different teams of studying different classes. So for example, the radio pulsars, supernova remnants, etc. And so we're going to be looking at 7 different classes and several examples of those classes, so that we get a good preliminary survey of what polarization is out there.
The extreme environments created by black holes are an opportunity to study many other phenomena. Neutrinos, the most abundant particles in the universe, have almost no mass and very rarely interact with matter. They seem to be generated in extreme objects like exploding stars and the fast particle jets ejected by supermassive black holes. Colliding black holes are another event closely watched, as they generate gravity waves that ripple through space-time and can be detected here on Earth. Another recent event detected was the flipping of the magnetic field surrounding a massive black hole. The reversing polarity caused the visual brightening of the material surrounding the black hole and the reduction of its X-ray emissions. During this time, the X-ray corona disappeared, and only when the flipped magnetic field gained strength did the X-rays emissions recover. Another black hole has been observed devouring a star that wandered too close. The ejected superfast jets of material interacting with nearby dust clouds and aiding to form planets within the material. These singularities appear to be an intrinsic part of both the destruction and creation of stars and planets. While we don't have all the answers, discoveries like this one set us on a path to understanding more about the universe. We have looked up to the stars and galaxies in awe and wonder for millennia, trying to understand our place in the universe. Current technology is enabling us to see further and farther back in time with much more detail than ever. The next generation of orbiting telescopes is soon to enter service. Who knows what giant leap they will make in our understanding of the universe. Since its launch in 2013, ESA's Gaia Observatory has been constantly mapping our galaxy, creating the most accurate and complete multi-dimensional map of the Milky Way. This latest observational dataset has been released and contains even more and improved information about almost 2 billion stars, solar system objects and extragalactic sources. Our Sun travels at 240 kilometers per second around the galactic center and will take 220 million years to complete one orbit. The Gaia dataset includes stellar positions, stars' distances, and motions across the sky, plus color information, and most significantly, the radial velocities for 33 million stars within the Milky Way. This allows astronomers to create the most accurate and complete multi-dimensional map of our astronomical neighborhood. Another novelty in this dataset is the largest catalogue yet of binary stars in the Milky Way, which is crucial to understand stellar evolution. At the Observatoire de Paris in Meudon, Paris, France, scientists form part of the Data Processing and Analysis Consortium, some 400 scientists from 20 countries who are responsible for the processing of Gaia's data with the final objective of producing the Gaia catalogue.
So Gaia is extremely important for all fields of astronomy. The Gaia catalogues, that results contain a huge amount of information that will provide the material for the work of astronomers in around the world and for many, many years.
With each new release, the observed stars, solar system objects and extragalactic objects increase, and many more details are added to what is already the most detailed overview of our galaxy.
So Gaia is an incredible satellite which looks at the stars, which measure 1.8 billion stars, but obviously it goes from what is nearby, asteroids, up to very distant quasars. For these 1.8 billion stars, it's able to find their distance, their astrophysical parameters, their ID card in some sense. Up to now, Gaia had given already a lot of information about stars, but now it's going from astrometry, the position, motion of the stars, up to astrophysics, knowing the characteristics, the astrophysical parameters for nearly 500 million stars. It is able also to find a lot of variable stars, to classify them. It's able, of course, also to see what is variable in terms of position, and so it helps to find binary stars which move on the sky or on the spectrograph.
And this time we provide new measurements such as star brightness in the RVS spectral range, rotational velocities, atmospheric parameters, chemical composition, and the RVS spectra also provide information on the abundance of the interstellar material that is present between stars.
So Gaia is observing with astrometric instruments which measure the position of the objects, and from this position it gets the motion of the object with time on the sky. That's astrometry. Then Gaia measures also the light of the object, measure spectrophotometry for the object, and from this it can infer the color of the object, but also you can derive from that all the astrophysical parameters that you can get, like temperature, effective temperature, gravity, and so on. You can also infer what is the extension of light in the distance where it comes from the star to us. So the third instrument now is a spectrograph, which is able to see the spectrum of the star. And so when you see the lines of the spectra, you see at which speed the object is going towards us or and the other way around. Or when it's moving periodically, then you can detect through the motion of this radial velocity. That's the three main instruments of Gaia.
Even older than Gaia is the venerable Hubble Space Telescope. It too continues to contribute to the science of cosmology.
To my mind, the most important discovery from Hubble is the discovery of dark energy. There have been a lot of interesting discoveries, certainly. Certainly the fact that there are billions and billions of galaxies that we had no idea there were that many. The work that we were doing on exoplanets with Hubble has been interesting. I mean, Hubble has carried such a wide variety of results that it's hard to pick a single one, but I do feel the dark energy is the outstanding discovery. And what that means is simply that space We always thought that space would contract because gravity would pull it together. We knew it was expanding, but we thought the expansion would slow down. Well, instead, the expansion's speeding up. And that is a very exciting thing to me.
Because the Hubble Space Telescope is operating so well and is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe. One mystery is dark energy. That's the name just kind of plastered on this phenomenon that Hubble and other telescopes together, we found that the universe expansion has been accelerating for the last few billion years. Well, what is causing that? We don't know. It's something about a repulsive force that we may not fully understand or new physics that we don't fully understand. But Hubble was used along in complement with some telescopes on the ground to determine that the expansion of the universe is in fact accelerating by something we're now calling dark energy. And without Hubble, we would have not been able to make this detection, which is now a Nobel Prize-winning discovery.
This explains why the universe appears to be accelerating now, when it used to be slowing down because of gravity. So now the question is, well, is this a simple story or is it complicated? Is there more than one kind of dark energy? Has the dark energy itself changed over time?
So Hubble is now being used to refine even further that expansion rate of the universe in our current epoch, and trying to compare that to what might be predicted from looking at other measurements of the universe with other telescopes. Right now we're finding a discrepancy between what we might have expected and what we're actually measuring. So that's one realm where Hubble is really at the cutting edge of helping us understand, or at least open up, new mysteries of the universe.
Astronomers are still puzzling over dark matter and how it behaves. They have found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter makes up the bulk of a galaxy. The gravitational influence of dark matter is thought to tie the galaxies together in massive clusters. There is so much regular matter and dark matter concentrated in these clusters that their gravity magnifies and warps light from distant background objects. By studying how the light distorts the background galaxies, though, this gravitational lensing can help map where the dark matter is in galaxy clusters. Images of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Soon to be launched, ESA's Euclid mission aims to investigate this dark matter, dark energy, and the expanding universe in even greater detail. Euclid will image billions of galaxies with unprecedented accuracy out to a distance of 10 billion light-years. These measurements will enable astronomers to improve their understanding of the expansion of the universe and the growth rate of cosmic structures.
Euclid is a cosmology mission. It will study and try to better understand the geometry and the nature of the dark matter and dark energy, which is the peculiarity of Euclid. It's a telescope that will scan the sky with an accuracy that is unprecedented. So this is really something that no other spacecraft did before. This will allow to get additional information and to better understand the story and for the expansion of the universe and the growth on the cosmic structure.
Euclid carries a 3-mirror anastigmat design. The primary mirror is 1.2 meters in diameter. This type of design allows for a greater field of view, covering the visible wavelengths and simultaneously near-infrared spectroscopy and photometry.
It was a very important milestone because it's somehow the starting point of a new phase of the project, because so far the two parts that you can see, the upper part that is the payload module and the lower part that is the service module, have been developed and tested separately. So today with the mating we start a following phase, the next phase, with both the two main constituents of the Euclid spacecraft are together.
Indeed, this is a completely new design with a lot of challenges involved with this mission, and we have put together a team of about 120 companies in Europe, which are working together in good synergy for several years, and we are very proud of the results achieved today.
The mission is designed for a 6-year lifespan. However, an extension of a further 5 years is contemplated, dependent on the spacecraft's onboard resources.
With the mating today of the telescope with the service module, we achieve a major milestone in the integration of the flight satellite. It has been a long journey because the two elements have been developed independently for several years, and now for the first time they are mated together, and this makes us very proud of the achievement.
So the telescope was already delivered here in October last year and was put in the clean room on the fixture, ready to be mated. In the meantime, we finished the work to be done on the remaining part of the satellite, which is here. And today we released the telescope from that foundation and we move it to the SVM by crane. It is a very dedicated operation because the tolerances or the budget we have for the mechanical stresses is very small. So it's a very fragile telescope because it needs to be light. So it's quite fragile. So for this operation, there was a tight allocation for the stresses. And the stresses they measured at every step on the feet which support the satellite on 6 points.
Next step after this mating will be the integration of the solar array sun shield, which will happen around May this year. And at that point, the satellite will be in full flight configuration. And at that point, we will go to Cannes to conduct the environmental test campaign for about 6 months. The objective is to have the satellite completely integrated and validated at the beginning of next year.
After the mating, the next step will be the finalization of all the connection, electrical testing. Then in front of the telescope will be installed the sun shield and the solar array, and after that the eye gain antenna. Then the test campaign will start in Cannes. The full spacecraft will be tested in environmental condition, and at the end it will be ready to be shipped to Kourou for the launch campaign.
Launching around the same time as Euclid is NASA's SphereX mission. It will survey hundreds of millions of galaxies near and far, some so distant their light has taken 10 billion years to reach Earth. Also, it will search for water and organic molecules within the Milky Way.
SphereX is NASA's latest Explorer mission in astrophysics. It's a small telescope, but it has this unique and powerful capability of doing spectroscopy everywhere.
We are going to survey the entire celestial sphere and collect a data set that will help us answer 3 fundamental science questions.
It's going to tell us about the origin of the universe, the birth and formation history of galaxies, and the abundance of essential molecules such as water in the early stages of star and planet formation.
The great thing about SphereX is not only will we view the entire sky 4 times, but we will see it in nearly 100 near-infrared colors. And that's really never been done before.
According to our current understanding of the universe, we think that in the very earliest times, and I'm talking here a fraction of a second, much less than a nanosecond, the universe appeared to have gone through an accelerating expansion called inflation. And this is really a profound idea, and we're very interested to test it. And so one way to do this is to look at how matter is distributed over the universe. We want to map hundreds of millions of galaxies in 3 dimensions. What Spherix does, in addition to mapping out all these galaxies, is we cover the whole sky. So we can measure these galaxies over the largest part of the range we can see, which is the entire sky. And we want to cover the full range of distances from today to as far back as we can see.
We know there are about 100 billion galaxies in the universe, maybe more, but we still don't have a good understanding how these galaxies came to be. Did they all form at the same time? Did they change in size and luminosity or brightness over time? So the intent with Spherix is for us to figure out the formation history of galaxies, where do they exactly form, and how do they grow over cosmic time. And that information is crucial for us because that'll allow us to separate various theories we have right now on the formation and growth of galaxies.
Spherix will also identify targets for more detailed study by NASA's James Webb Space Telescope and the future Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope is set to launch atop a SpaceX Falcon Heavy within the next few years. It will capture images unlike any satellite before it. The Roman Space Telescope will have the same image resolution as Hubble, but with 30 years of technological advancement, will cover an area 100 times larger. Roman will also view the sky in carefully selected wavelengths of infrared light. This will allow scientists to see through the obscuring dust to reveal hidden stars and watch the growth of galaxies over the last 10 billion years. Because Roman will be seeing further back in time, accurate measurement of distant stars is critical. A small galaxy close in looks similar to a large galaxy farther out. One method used by astronomers to gauge distances is something called a standard candle. A standard candle is a type of stellar object or event that emits a specific known amount of light. This works because light sources appeared predictably dimmer the farther away they are. So, for further distances, astronomers have to rely on the brightest of stars or events, in particular exploding stars called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. The white dwarf accumulates mass from its partner and eventually explodes, giving off a set amount of light. These beacons then allow scientists to accurately predict their distances. Roman will also use its broad view to search for planets around other stars in our galaxy. It will be fitted with a coronagraph which reduces the light coming directly from the star to separate it from the light reflected by the planet. The Roman Space Telescope's coronagraph doesn't block the star's light. It uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly disappear, revealing brighter planets. Advanced software processes this data. further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own. The Nancy Grace Roman Space Telescope will also look for the fingerprint of dark matter and dark energy in the distant reaches of the universe. With an unprecedented combination of breadth and depth, it will open a new era in observing and understanding our universe.